please subscribe to support the channel. Across the vastness of the universe, one shape seems to repeat itself over and over again. The sphere. From planets and stars to tiny droplets of water, roundness is everywhere. But why? This universal shape isn't just a coincidence or a matter of aesthetics. It's a direct result of the laws of physics. Whenever forces like gravity, pressure, and energy act freely on matter, they naturally pull it into the most balanced, efficient form possible, a sphere. Whether it's the sun and the depths of space, or a raindrop falling through the air, roundness represents equilibrium, symmetry, and nature's preference for stability. It's the shape that emerges when everything finds perfect balance. When we talk about roundness, it's easy to picture something simple, maybe a ball, a circle, or a planet seen from space. But in physics and geometry, round is not just about appearance. It's a description of symmetry, balance, and uniformity. To truly understand why the universe tends to create round things, we have to first understand what being round actually means, and how that concept changes depending on scale and dimension. In everyday language, we use round to describe things that don't have sharp corners or edges. A smooth pebble, a droplet of rain, or the curve of the moon all feel round to us because their shapes appear continuous and even. But scientifically, there's a big difference between a circle, a sphere, and a generally rounded form. A circle is a two-dimensional concept. It's the set of all points that are exactly the same distance from a single point, the center, on a flat plane. Imagine drawing with a compass. The fixed metal point marks the center, and the pencil traces out the edge at a constant radius. Every point on that boundary lies at an equal distance from the center, forming perfect symmetry in every direction. A sphere, on the other hand, is the three-dimensional extension of that same principle. It's what happens when that perfect circle expands into every direction in space. Every point on the surface of a sphere is equidistant from its center. That means no matter where you measure, from pole to equator or across any diagonal, the distance is the same. In pure mathematics, a sphere is a flawless geometric object, perfectly smooth and perfectly balanced in all dimensions. Then there are rounded forms, which are objects that are not perfectly spherical, but still exhibit curvature without sharp angles. The Earth, for example, is often described as a sphere, but it's actually an oblate spheroid, slightly flattened at the poles and bulging at the equator due to its rotation. The same applies to most planets, moons, and even stars. They are round in a general sense because gravity molds them into roughly spherical forms, but other forces like spin, temperature differences, or tidal stretching introduce small imperfections. Roundness, therefore, is not just a shape, it's a result of how forces act on matter. When we say something is round, we're really saying that it's been shaped by evenly distributed forces that pull toward a common center. Whether it's the circular ripples spreading across a pond or the spherical curve of a planet, roundness signals that energy has found a balanced configuration. In a sense, the round form is nature's way of saying the forces acting here are equal in all directions. But this equality doesn't come easily. It depends on the balance between external influences and internal resistance. A lump of rock on an asteroid, for instance, doesn't have enough gravity to pull itself into a sphere, so it remains jagged. But once an object grows massive enough, when gravity becomes stronger than the material's own rigidity, it begins to round out. That's when we see the transition from irregular rocks to planets and stars that are nearly perfect spheres. Roundness also reflects something deeper about the universe's preference for symmetry. Mathematically, the sphere is the most symmetrical shape in existence. It looks the same from every angle and direction. There's no privileged point or orientation. This symmetry is why physicists often use spherical coordinates when describing gravitational fields, electric fields, or the distribution of matter in stars. When forces act equally in all directions, the natural result is spherical geometry. Even in small, simple systems, roundness emerges when forces equalize. A drop of water floating in space, for instance, will automatically form a sphere because the surface tension in the liquid pulls all its molecules inward equally, minimizing surface area for a given volume. That's the key. Roundness is not arbitrary, it's the most efficient shape. It uses the least amount of energy to enclose the most amount of space. We also need to recognize that round doesn't always mean perfectly smooth or mathematically precise. A slightly flattened planet, a cratered moon, or a rotating gas giant like Jupiter, all are still considered round in an astrophysical sense. Their overall geometry is dominated by a spherical tendency, even if local irregularities distort their surfaces. Roundness, therefore, is not just about perfection, it's about dominance. Gravity and pressure dominate over structure and rigidity, enforcing a near spherical form. If we were to strip everything down to the most basic truth, we could say this: roundness is the physical manifestation of symmetry under equal forces. It's a universal language that connects droplets of water, living cells, planets, stars, and galaxies, all shaped by the interplay of forces that prefer uniformity. Once you see that connection, you begin to notice roundness everywhere, not as coincidence, but consequence. As we move forward, understanding this definition gives us the foundation to explore the why. Why does gravity create spheres, and why does it always seem to prefer this particular shape above all others? The answer lies in one of the most fundamental forces in the cosmos, one that governs everything from the fall of an apple to the birth of a star. That force is gravity, and it is the invisible sculptor that shapes the universe into its round forms. Gravity is the quiet, invisible architect of the cosmos, the universal sculpture shaping everything from the tiniest dust grains in space to the grandest stars and galaxies. To understand why so many things in the universe end up round, we must understand gravity's role not just as a force of attraction, but as a force of equilibrium, one that constantly seeks balance. Gravity doesn't play favorites. It pulls equally in all directions, always aiming toward the center of mass. And it's this perfectly even pull that gives rise to roundness.
Every object with mass exerts gravity. You, me, the Earth, even a small rock, all have gravitational fields. But for most small objects, that pull is minuscule, overwhelmed by the rigidity of their materials or the electromagnetic bonds between their atoms. Only when enough mass accumulates does gravity begin to dominate, bending and reshaping matter according to its will. Once an object becomes massive enough, gravity overpowers the internal strength of its material and starts pulling every part of it inward, toward its center of mass. This process, given enough time, molds the object into a sphere. Imagine a loose cloud of dust and gas floating in the emptiness of space. Each grain exerts a faint gravitational pull on every other grain. Over millions of years, those particles drift closer, clumping together, growing heavier, and as the mass increases, so does the strength of gravity. This self-reinforcing process, called accretion, continues until gravity becomes strong enough to reshape the growing body into a more compact form. At first, it might look irregular or lumpy, but as more material gathers, gravity begins to smooth out those bumps. The uneven parts experience slightly stronger inward pulls, slowly collapsing until the entire mass approaches a balanced, rounded state. Why does gravity make things spherical? Because the sphere is the only shape where all points on the surface are the same distance from the center. This means gravity acts equally everywhere, pulling matter inward from all directions at once. If an object were shaped like a cube or a pyramid, the corners and edges would be farther from the center than the faces. Gravity would then pull harder on those distant corners, slowly eroding the shape until the differences evened out. Over time, what remains is a smooth, symmetrical sphere, the configuration where gravity is perfectly balanced at every point on the surface. This process happens on cosmic scales too. Planets form as rotating disks of dust and gas around young stars. Within those disks, smaller particles collide and stick together, forming larger and larger bodies known as planetesimals. Once a planetesimal reaches a few hundred kilometers in diameter, its own gravity becomes powerful enough to overcome the rigidity of rock or ice, forcing the material into a rounded shape. This is how planets, moons, and even some large asteroids become spherical. It's the universe's way of saying, you've gathered enough mass, now gravity takes control. Stars, too, are shaped by gravity's insistence on symmetry. When a massive cloud of hydrogen gas collapses under its own gravity, it heats up, ignites nuclear fusion, and stabilizes as a luminous sphere. The balance between the inward pull of gravity and the outward pressure from fusion defines the star's size and shape. Without gravity's equal inward pull, a star could never hold its structure. It would simply disperse into space. On a more conceptual level, gravity doesn't just create spheres, it maintains them. Every particle within a spherical body is pulled toward the center, ensuring that if any part bulges outward, gravity immediately acts to correct it. This constant tug-of-war keeps planets round even after billions of years of rotation, impacts, and tectonic shifts. The same principle applies to stars, whose plasma flows freely, allowing gravity to maintain near-perfect roundness despite their constant internal motion. There's also something deeply elegant about how gravity sculpts these forms. It doesn't carve with precision or intent. It doesn't need tools or guidance. It simply acts according to one rule. Mass attracts mass. And from that one rule, entire worlds emerge. It's the same process that governs the shape of galaxies, black holes, and even clusters of galaxies. The deeper you look, the more you realize that gravity is the universe's greatest artist, and its preferred brushstroke is the curve. It's worth noting that gravity doesn't act in isolation. Other forces can distort or resist it, such as a planet's spin, magnetic fields, or external tidal forces from neighboring bodies. But gravity always strives for one outcome: equilibrium. The sphere is gravity's version of rest, the configuration where every atom is as close as it can be to the center without collapsing inward. When you hold a globe in your hands or look up at the full moon, what you're seeing is the culmination of countless years of gravitational balance. You're seeing matter that has surrendered completely to gravity's pull, yielding to a state of uniformity and peace. The same force that keeps your feet on the ground has over cosmic time sculpted planets, stars, and even the universe's large-scale structures into shapes of smooth, elegant symmetry. In short, gravity's role in creating roundness is both simple and profound. It acts as a universal equalizer, pulling everything inward toward the center of mass until all imbalances disappear. When gravity has enough strength to overcome the resistance of material forces, the inevitable result is a sphere, the most stable and efficient form in the cosmos. And yet, as powerful as gravity is, it doesn't act alone in determining whether something becomes round or stays irregular. The size of the object, how massive it becomes, plays a crucial role in deciding whether gravity can truly take charge or whether other forces will win out. That's where our next journey takes us, understanding how size determines shape and why the small and the massive live under different rules. When it comes to roundness in the universe, size truly matters. It's not just about what something is made of, but how big and massive it becomes. The difference between a lumpy asteroid and a smooth, spherical planet isn't simply composition. It's a question of scale, of how strong gravity is relative to the object's internal strength. At small scales, an object's material rigidity dominates. At large scales, gravity takes over. This delicate balance between structural resistance and gravitational pull determines whether something stays jagged and irregular or becomes gracefully round. Let's start with the simplest example, a rock. A rock sitting on Earth's surface has its own gravity, yes, but that gravity is vanishingly small. Its atoms are held in place by strong chemical bonds, the electromagnetic forces that define its rigidity. Gravity's pull between any 2 points within that rock is far too weak to overcome these molecular forces. That's why the rock can keep its shape. No matter how long it sits there, it won't suddenly collapse into a sphere. Its self-gravity simply isn't powerful enough to reshape it.
Now take that rock and imagine scaling it up, not just to the size of a mountain, but to hundreds of kilometers across. At a certain point, the accumulated mass begins to make a difference. Gravity, which increases with mass, starts to tug on the object more strongly from every direction. As the mass grows, the gravitational pressure at the core increases, while the material's rigidity remains relatively constant. Eventually, a threshold is reached, a point where gravity becomes stronger than the material's ability to resist deformation. Once that happens, the body starts to compact and smooth itself out, collapsing under its own weight into a nearly spherical shape. This critical point is known as the potato radius. It's the size at which gravity begins to dominate over the material strength of the object. For rocky bodies, this radius is roughly around 200 to 300 kilometers. For icy bodies, which are less rigid, the threshold is a bit smaller, closer to 150 to 200 kilometers. Below these sizes, objects tend to look irregular, like jagged potatoes tumbling through space. Above that threshold, gravity gradually smooths out the rough edges, rounding the object into a more symmetrical form. That's why many asteroids, such as Eros or Itokawa, have bizarre, elongated shapes. They're simply too small. Their gravity isn't strong enough to pull their material into balance. But look at Ceres, the largest object in the asteroid belt. At nearly 940 kilometers in diameter, it's large enough that gravity has taken command, shaping it into a near-perfect sphere. The same applies to Europa, Enceladus, and Ganymede, moons that have crossed that gravitational threshold and surrendered their forms to roundness. For smaller bodies, like Phobos and Deimos, the two moons of Mars, gravity's grip is weaker. These moons are only a few dozen kilometers across, and their lumpy, cratered surfaces reveal how rigidity has the upper hand. They're frozen snapshots of what matter looks like before gravity gets its way, a glimpse of the early stages of formation before mass and symmetry reshape everything. This interplay between size and gravity explains why the universe has such a variety of shapes. The difference between a tiny asteroid and a massive planet isn't just scale, it's an entirely different physical regime. On small scales, the electromagnetic forces between atoms and molecules define structure. On large scales, those forces become negligible and gravity's collective pull takes control. Think of it as a cosmic hierarchy of power. For a pebble, electromagnetic bonds rule supreme. For a mountain, those bonds still win, keeping the rock intact despite the mountain's immense weight. But for a planet, something the size of Earth or larger, gravity overwhelms all internal strength. Even the toughest rock yields. The materials may compress, deform, and even melt under the pressure, until everything settles into a rounded equilibrium. This scaling effect also explains why gas giants like Jupiter and Saturn are so extraordinarily spherical. Made mostly of hydrogen and helium, their internal rigidity is practically zero. Gravity can easily mold these massive, fluid bodies into shapes that are nearly perfect spheres. In fact, Jupiter is so massive that its equatorial and polar radii differ by only a small fraction despite its rapid rotation. The sheer magnitude of its gravity smooths out nearly every irregularity. Conversely, consider the tiny irregular worlds of the asteroid belt, or Kuiper belt, regions filled with remnants from the early solar system. Many of these objects never grew large enough to cross the gravitational threshold, and so they remain frozen in awkward, misshapen forms. Their jagged edges, long ridges, and strange peanut-like shapes are records of incomplete formation, worlds that gravity never had enough time or mass to perfect. It's fascinating to realize that this simple principle, the contest between gravity and rigidity, defines so much of the universe's visual diversity. It tells us not only why some objects are round, but why others aren't. It sets the boundary between planets and asteroids, between moons that are spheres and those that are lumps of rock. In planetary science, this difference even forms part of how we define what a planet is. According to the International Astronomical Union, one of the defining characteristics of a planet is that it must be massive enough for its self-gravity to pull it into hydrostatic equilibrium, a fancy term for saying it's rounded under its own weight. That's the line between a planet and a planetesimal, between a world and a rock. So when we say that size matters, we're really saying that mass determines destiny. Small objects live under the rule of rigidity, frozen in the jagged shapes of their birth. Large objects surrender to gravity, reshaping themselves into the smooth, rounded harmony that dominates the cosmic landscape. And as we transition from the small to the immense, from asteroids and comets to fully formed planets and blazing stars, we begin to see how gravity, once strong enough, becomes the ultimate sculpture. It doesn't just round objects, it defines them. When mass grows to the point where gravity becomes irresistible, the universe starts crafting perfect spheres. And with that, the story of planets, moons, and stars truly begins. Once an object grows large enough, crossing that invisible threshold where gravity becomes the dominant force, something extraordinary happens. It transforms from a random collection of material into a world. The jagged edges smooth out, the irregular shapes collapse inward, and the object reorganizes itself into a state of perfect balance, the sphere. This is the moment when gravity fully takes command, reshaping everything according to its law of uniform attraction. And it's at this point that the universe begins to create the celestial bodies we recognize: planets, moons, and stars. When a young planet or star is forming, it begins as chaos, swirling dust, gas, and ice clumping together under mutual attraction. In those early stages, the shape is often uneven, fragmented, and turbulent. But as mass builds up, gravity strengthens exponentially. Remember, gravity increases not linearly, but with the square of distance, meaning that every new bit of mass dramatically amplifies the overall pull. Once this gravitational force exceeds the internal rigidity or pressure differences within the object, all matter begins to move towards the center of mass. The result is an inward collapse that gradually erases asymmetry, rounding the object into a nearly perfect sphere.
Let's start with planets. Every planet you've ever seen, from Earth and Mars to Jupiter and Neptune, has gone through this process. Billions of years ago, these worlds began as dusty clumps within a protoplanetary disk surrounding a newborn star. As collisions between particles added mass, gravity started to reshape these bodies. The more material they gathered, the stronger the inward pull became, crushing and compacting the interior until the object reached hydrostatic equilibrium, the state in which gravitational forces pulling inward are perfectly balanced by the pressure pushing outward. At that point, the body achieves roundness. But that roundness doesn't come instantly. In the violent early solar system, planetesimals, those smaller, irregular precursors to planets, collided constantly, breaking apart and reforming. Some grew large enough to become spherical worlds. Others remained small and misshapen, trapped in the limbo of incomplete formation. Earth, for instance, formed from countless impacts and mergers. Each impact added mass, heat, and energy, melting the surface and allowing gravity to pull the molten material into a smooth, rounded form. Over time, even after cooling and solidifying, Earth retained its spherical shape because gravity continued to act equally in all directions, maintaining the balance. The same principle applies to moons. Some moons, like our own, are round because they have sufficient mass for gravity to dominate. Others, like Mars's tiny moons, Phobos and Deimos, remain irregular, shaped more by rigidity than by gravity. The distinction is once again a matter of scale. Mass decides whether an object can yield to the will of gravity. Then, when we scale up even further, we reach the stars, the ultimate expression of gravity's power. Stars begin their lives as enormous clouds of gas and dust floating in interstellar space. Over millions of years, these clouds collapse under their own gravity, forming dense cores. As the collapse continues, the material at the center grows hotter and denser until nuclear fusion ignites, the birth cry of a star. From that point onward, gravity and pressure enter into a delicate dance. Gravity pulls everything inward, while the energy from fusion pushes outward. This balance, known as hydrostatic equilibrium, is what keeps a star stable and, crucially, spherical. Because stars are made of plasma, hot, ionized gas, they don't resist deformation the way solid planets do. This means that gravity can mold them into even more perfect spheres than rocky worlds. A star's surface is fluid, so any irregularity is quickly smoothed out by gravity and internal pressure. The result is a form so round that even the most powerful instruments on Earth struggle to detect deviations from perfect symmetry. The Sun, for example, despite being a massive ball of turbulent plasma, deviates from a perfect sphere by less than 10 kilometers across its 1.4 million kilometer diameter, a difference of less than 1/10,000th of a percent. What's beautiful about this is that the same rule applies across vastly different scales and materials. Whether it's a rocky planet, an icy moon, or a blazing star, once gravity becomes dominant, the end result is always a sphere. It doesn't matter what the object is made of: rock, gas, metal, or plasma. The geometry of balance is the same. A sphere represents the shape where every point on the surface is equally close to the center of mass, meaning gravity acts uniformly in every direction. Any other shape would create imbalances. Parts that are farther from the center would feel less gravitational pull, causing the object to adjust until the equilibrium is restored. This universal process is why the night sky looks the way it does. When you gaze up at the moon or observe the glowing disk of the sun, you're witnessing gravity's handiwork, the cosmic tendency towards symmetry. Every round world tells a story of mass, pressure, and time conspiring to achieve balance. Even the gas giants, Jupiter, Saturn, Uranus, and Neptune, are nearly perfect spheres, with only slight bulging at their equators due to rapid rotation. Their enormous mass gives gravity overwhelming authority, forcing their hydrogen and helium layers into smooth, continuous curves. Roundness, then, isn't just a feature of planets and stars, it's their defining state. It marks the moment when chaos gives way to order, when scattered dust becomes a world, when a collapsing cloud becomes a star. In a sense, it's the universe's way of declaring that a body has achieved stability. Once gravity takes over completely, there's no other possible shape that satisfies the symmetry of its pull. So when we say that planets and stars are round, we're really describing the endpoint of a cosmic journey, the natural destination of matter under the influence of gravity. Every sphere in space is a monument to this balance, to the point where inward and outward forces meet in perfect harmony. And that harmony has a name: hydrostatic equilibrium. It's the physical condition that explains why celestial bodies become round, why they maintain that roundness, and how their internal structure holds together. In the next segment, we'll dive deeper into this concept, exploring how gravity and internal pressure work together to create and preserve the spherical forms we see throughout the cosmos.
At the heart of every round planet and star lies a state of balance so perfect, so delicate, that it defines the very structure of the cosmos itself: hydrostatic equilibrium. This term may sound complex, but it describes one of the simplest and most elegant ideas in physics: the point at which gravity pulling inward and pressure pushing outward exactly cancel each other out. It's the invisible handshake between two opposing forces that together create stability, and as a direct result, roundness. To understand hydrostatic equilibrium, imagine standing inside a planet. The deeper you go, the stronger the pull of gravity becomes, because more and more of the planet's mass lies above you, pressing down. At the same time, the material inside the planet, whether rock, metal, or gas, resists being crushed. It pushes back with an equal and opposite force called internal pressure. When these two opposing forces balance perfectly at every layer of the object, the system reaches hydrostatic equilibrium. This balance keeps the planet from collapsing under its own gravity or expanding uncontrollably. It's what allows worlds to hold their shape over billions of years. In a sense, hydrostatic equilibrium is the universe's version of peace. On one side is gravity, the relentless inward pull that tries to compress everything into a smaller and smaller space. On the other side is pressure, born from heat, atomic motion, and the inherent resistance of matter, which pushes outward, trying to expand. When these two forces meet and neither wins, they form a stable structure, a sphere. And it's not just any sphere, but one shaped precisely by the balance of those internal and external forces. Let's take a planet like Earth as an example. Deep within Earth's core, the pressure from the overlying layers is immense, millions of times greater than the pressure at the surface. Gravity is constantly trying to pull all that material inward toward the center. But the dense metals and silicate rocks in the core push back with equal strength. This perfect counterbalance keeps the planet from collapsing. Every layer, from the molten outer core to the solid mantle and crust above it, exists in this dynamic equilibrium. The result is a self-sustaining structure, round because the inward pull is identical in every direction. Now consider the Sun, an even more dramatic demonstration of hydrostatic equilibrium. In the Sun, gravity is unimaginably strong, pulling billions of tons of plasma inward every second. Without an opposing force, the Sun would collapse under its own weight in an instant. But deep inside, nuclear fusion provides the necessary counterpressure. As hydrogen atoms fuse into helium, they release tremendous amounts of energy, producing radiation that pushes outward. That outward pressure perfectly balances the inward pull of gravity, creating a state of equilibrium that defines the Sun's size, temperature, and shape. This balance is so precise that even a slight disruption, say a change of just a few percent, could alter the Sun's structure entirely, either causing it to expand or collapse. Hydrostatic equilibrium doesn't just make objects round, it determines how they live, evolve, and die. In stars, it governs every phase of their life cycle. When a star exhausts its nuclear fuel, the outward pressure from fusion ceases and gravity wins. The star collapses, often violently, leading to phenomena like supernovae, neutron stars, or black holes. Conversely, when fusion begins anew in a young star, equilibrium is restored and the star stabilizes as a luminous sphere once again. This constant dance between gravity and pressure is the heartbeat of the universe, a rhythm that every star, planet, and gaseous world follows. For planets, the source of outward pressure isn't fusion, but the internal strength and temperature of their materials. In rocky planets like Earth, internal heat from formation, radioactive decay, and core activity provides thermal pressure. In gas giants like Jupiter, it's the compression of hydrogen and helium that generates immense internal pressure, pushing outward just enough to counter gravity's inward pull. The result is a stable, nearly spherical planet that can persist for billions of years without collapsing or expanding significantly. What makes hydrostatic equilibrium so fascinating is how naturally it leads to spherical symmetry. Because gravity always points toward the center of mass, the opposing pressure must also act uniformly in every direction to maintain balance. If either force were stronger on one side, matter would move until equilibrium was restored, smoothing out any irregularities. This constant redistribution ensures that the body's shape remains round regardless of what it's made of. The larger and more fluid the object, the closer it approaches a perfect sphere. Even small deviations from equilibrium reveal themselves in fascinating ways. When planets rotate, for instance, centrifugal force slightly offsets gravity at the equator, causing a bulge, an effect we'll explore later when we talk about rotational flattening. But even then, the overall structure remains governed by hydrostatic equilibrium. The equatorial bulge isn't a failure of roundness, it's a new balance point between gravity, pressure, and rotational forces. In essence, hydrostatic equilibrium is the quiet architect of cosmic stability. It's why planets maintain their forms, why stars shine steadily for billions of years, and why celestial bodies tend to be round. It's not an imposed symmetry, it's an emergent one, born from the laws of physics seeking balance.
Without it, the universe would be filled with collapsing clouds and exploding masses, a chaotic realm with no stable worlds or stars. When you look at the sun rising on the horizon or see images of distant planets taken by spacecraft, what you're witnessing is the visual expression of this invisible balance. Every curve, every contour of those spheres is the outward sign of hydrostatic equilibrium, gravity and pressure locked in eternal harmony. But as perfect as this balance seems, it's never absolute. In the next stage of our exploration, we'll see that even though gravity and pressure work tirelessly to create roundness, other forces, such as rotation, can subtly distort that perfection. The result? Worlds that are not quite perfect spheres, but beautifully flawed ones, flattened at the poles, stretched at the equator, and endlessly shaped by motion. Although gravity and pressure work together to sculpt planets into nearly perfect spheres, the story of planetary shape doesn't end there. In reality, no planet in the universe is a perfect sphere. Each one bears subtle and sometimes dramatic distortions caused by motion, rotation, and internal structure. The most significant of these influences is rotation, the simple fact that planets spin. This rotation introduces a new force into the delicate balance of hydrostatic equilibrium, one that slightly reshapes worlds from ideal spheres into oblate spheroids, bulging at the equator and flattening at the poles.
To understand why, we need to look closely at what happens when a planet spins. Every point on the planet's surface is in motion, rotating around the axis that runs from pole to pole. Points near the poles move very little. They're close to the axis and essentially spin in place. But points near the equator travel the farthest distance during each rotation, thousands of kilometers per day in Earth's case, and therefore experience much stronger centrifugal force. This apparent outward force acts opposite to gravity. While gravity pulls everything toward the center, rotation pushes matter outward, perpendicular to the axis of rotation. The result is a tug-of-war between these two influences. Gravity wants to make the planet perfectly round, pulling everything toward the center. Rotation wants to fling material outward at the equator. When the two forces balance, the planet reaches a new equilibrium shape, slightly squashed at the poles and slightly stretched around the middle. This shape is what we call an oblate spheroid. Still round, but imperfectly so. Take Earth, for instance. Our planet spins once every 24 hours, and that steady rotation is enough to cause a noticeable, though small, equatorial bulge. The diameter across the equator is about 12,756 kilometers, while the diameter from pole to pole is roughly 12,714 kilometers, a difference of about 42 kilometers. That may sound tiny compared to Earth's total size, but it's enough to make our planet distinctly oblate. It's also the reason objects weigh slightly less at the equator than they do near the poles. Centrifugal force counteracts a small fraction of gravity's pull there. This bulging effect becomes even more pronounced on planets that rotate faster. Jupiter, for example, completes one rotation in just under 10 hours, despite being over 11 times wider than Earth. Its rapid spin generates tremendous centrifugal force, enough to stretch its equatorial diameter to about 9,925 kilometers greater than its polar diameter. That's nearly a 6.5% difference, large enough to be easily visible in photographs. From space, Jupiter looks like a slightly flattened ball, a visual reminder of how rotational speeds sculpt shape. Saturn pushes this even further. It spins at a similar rate, but is composed primarily of hydrogen and helium, light gases that are far more compressible than rock or metal. This makes Saturn even more susceptible to deformation from rotation. Its equatorial diameter exceeds its polar diameter by nearly 10%, giving it one of the most noticeable oblate shapes in the solar system. If Saturn spun any faster, parts of its atmosphere at the equator would begin to escape into space, unable to resist the outward force. Rotation doesn't just affect gas giants. Even smaller rocky planets and moons exhibit subtle equatorial bulges. Mars, for instance, rotates once every 24.6 hours, roughly the same rate as Earth, and displays a small but measurable flattening at the poles. The Moon, by contrast, spins so slowly, once every 27 days, that the effect is negligible, allowing it to remain almost perfectly spherical.
The faster a planet or moon rotates, the more its shape departs from perfect roundness. But rotation's influence goes deeper than just visual shape. It also affects the internal structure and dynamics of a planet. Inside Earth, for example, rotation contributes to the slight redistribution of mass, affecting the flow of molten rock in the mantle and the behavior of the liquid outer core. These movements, in turn, influence Earth's magnetic field. In gas giants, rapid rotation causes complex banding and storm systems as centrifugal effects and fluid motion interact within their vast atmospheres. Thus, the planet's oblate shape is not merely cosmetic, it's a physical manifestation of its internal dynamics and rotation rate. There's another fascinating aspect of this phenomenon. Rotation actually defines the limit of how fast a planet can spin before it begins to break apart. If a planet spins too rapidly, the centrifugal force at the equator can exceed gravitational attraction, causing the planet to lose mass or even tear apart. Astronomers refer to this as the breakup velocity, the maximum rotation speed an object can sustain while remaining intact. For rocky planets, that threshold is extremely high, but for gaseous planets, it's much lower due to their lower density. Rotation also interacts with gravity to define the shape of stars. While most stars appear perfectly round to the naked eye, many of them rotate at incredible speeds, causing measurable equatorial bulges. A prime example is Achernar, a star in the constellation Eridanus, which spins so fast that its equatorial diameter is nearly 50% greater than its polar diameter. In this case, hydrostatic equilibrium still applies, but rotation modifies it, creating a new equilibrium where the outward and inward forces balance differently across latitudes. It's important to realize that these deviations from perfect roundness are not flaws. They're refinements. Rotation adds a layer of complexity to the pure symmetry of gravity, transforming the ideal sphere into something dynamic and alive. A spinning planet is not static. It's constantly redistributing its mass, balancing between forces and adapting its shape to match its internal energy and motion. The result is a kind of living geometry, one that reflects both the calm of equilibrium and the energy of motion. So, when we look at planets like Earth, Jupiter, or Saturn and notice their subtle flattening, we're seeing evidence of motion, the mark of time and energy imprinted on their shapes. The sphere, though nature's favorite form, is always slightly modified by the universe's dynamism. Planets spin, stars rotate, and even galaxies turn on colossal scales. Roundness, then, isn't static perfection, it's the balance of forces in motion. As we move outward in our exploration, we find that not every object has enough mass or spin to reach this balanced, rounded state. Smaller bodies, like asteroids and comets, live in a very different regime, where gravity can't overcome rigidity, and motion often leads to irregular, lumpy shapes. These small wanderers remind us what planets once were, rough beginnings, waiting for gravity to smooth them into spheres. When we shift our gaze from the grand, rounded worlds of the planets and stars to the humbler wanderers of the solar system, asteroids, comets, and small moons, we see a very different picture of what gravity can and can't do. These smaller bodies are the irregular ones, the cosmic misfits that never quite achieve the smoothness and symmetry of the planets. Their shapes are strange, jagged, sometimes even comical. Elongated like peanuts, flattened like pancakes, or twisted into forms that look more like broken shards than celestial bodies. And the reason is simple yet profound. Their gravity isn't strong enough to smooth them out. Gravity, as we've explored, is the ultimate sculptor of roundness. But like any sculptor, it needs strength, the kind that comes only from mass. For small objects, there simply isn't enough mass to generate the gravitational pull required to overcome the rigidity of their materials. The internal molecular and atomic bonds, the electromagnetic forces that hold rock and ice together, dominate instead. So rather than yielding and flowing toward an equilibrium shape, these smaller worlds stay stiff, preserving their irregular outlines for billions of years.
Think of the early solar system, roughly 4.5 billion years ago. In those days,
space was filled with an enormous population of rocky and icy fragments left over from the birth of the planets. These fragments collided, broke apart, and occasionally merged, forming what we now call asteroids and comets. Most of them never grew large enough for gravity to take control. They remained small, tens or hundreds of kilometers wide, far below the threshold where self-gravity could reshape them. Over time, impacts, fractures, and thermal stresses carved their surfaces into bizarre, uneven forms that remain frozen in time to this day. Take asteroid Eros, for example, a world visited by NASA's Near Shoemaker spacecraft. Eros is elongated, measuring about 34 kilometers long and 11 kilometers wide, looking more like a potato than a planet. Its surface is littered with craters, grooves, and ridges, evidence of countless collisions. Gravity on Eros is so weak that a person could easily jump off its surface and never come back. At this scale, gravity simply doesn't have the power to pull the rock into a smoother, rounder shape. Or consider Itokawa, another small asteroid famously studied by Japan's Hayabusa mission. Itokawa is just 535 meters across, less than a third of a mile. Its shape resembles a lumpy, peanut-like blob made of rubble loosely held together by weak gravity. In fact, Itokawa is a rubble pile asteroid, meaning it's not a single solid rock at all, but a collection of boulders and dust clumped together. If you could stand on it, you'd be standing on a mountain of debris, held together more by the gentle touch of gravity than by structural strength. Then there's 67P Churyumov-Gerasimenko, the comet visited by the European Space Agency's Rosetta mission. With its two-lobed rubber duck shape, it offers a striking example of how irregular smaller bodies can be. Its weak gravity allows it to maintain this shape, one that likely formed when two separate bodies gently collided and stuck together billions of years ago. A planet-sized object would never sustain such an uneven form. Gravity would immediately pull it into a sphere. But in the delicate microgravity environment of a comet, asymmetry can last indefinitely. This same principle applies to many small moons scattered throughout our solar system. The large moons like Earth's moon, Ganymede, Titan, and Europa are round because they are massive enough for gravity to dominate. But smaller moons orbiting Mars, Jupiter, Saturn, or Uranus often look more like captured asteroids than miniature planets. Phobos and Deimos, the two tiny moons of Mars, are prime examples. Phobos is only about 22 kilometers across, and Deimos is even smaller, around 12 kilometers. Their gravity is so feeble that a baseball thrown at escape velocity could leave the moon's surface forever. Both have irregular, cratered shapes, too small and too rigid to smooth themselves into spheres. When scientists talk about why these bodies are irregular, they often refer back to the concept of the potato radius, which we mentioned earlier. For rocky bodies, this is roughly around 200 to 300 kilometers in diameter, the point where self-gravity becomes strong enough to overcome material strength and force the object into hydrostatic equilibrium. Anything smaller than that remains irregular. For icy bodies, which are less rigid, the threshold is smaller, roughly around 150 to 200 kilometers. This is why small icy moons like Mimas, around 396 kilometers across, are spherical, while rocky asteroids like Vesta, 525 kilometers, are only partially so. Not quite perfect spheres, but closer to round than their smaller counterparts. These irregular shapes tell a story, one written in collisions, gravity, and time. Each dent and ridge is a record of the solar system's violent past, when countless fragments crashed together in the chaotic early days of planetary formation. The smaller the body, the more vulnerable it was to being reshaped by impacts rather than by gravity. So while large planets evolved into smooth, balanced worlds, the small ones stayed jagged, their forms frozen in the shapes that random chance gave them. But small size doesn't mean simplicity. These irregular worlds offer invaluable clues to the history of the solar system. Because their gravity is too weak to compress them or drive internal activity, they remain geological time capsules, preserving the original material and structure from the era of planet birth. The rock you might find on an asteroid could be virtually unchanged from when the sun first ignited. In a sense, their irregular shapes are a feature, not a flaw, evidence of their ancient, untouched state. When we see them up close, these odd shapes also change how we think about roundness in the universe. They remind us that roundness isn't guaranteed, it's earned. It's something that happens only when mass and gravity reach a critical threshold. Below that line, matter lives under a different regime, one ruled by rigidity and accident, rather than equilibrium. The universe's smaller bodies are snapshots of what the larger ones once were, before gravity had enough authority to impose symmetry. So while the big worlds, Earth, Jupiter, and the Sun, are round because gravity has completely triumphed, these small asteroids and moons are like unfinished works of art. They show us the early stages of creation before gravity's smoothing hand could finish its work. And yet, even in their irregularity, there's beauty, a raw, unpolished record of the forces that built everything we see today. In the next part of our journey, we'll look upward again, from the lumpy rocks and frozen fragments to the stars themselves. These enormous blazing spheres are the purest expressions of gravity and equilibrium, where the balance between inward and outward forces is pushed to cosmic extremes.
Stars, those luminous hearts of galaxies, the furnaces where all known matter is forged, are among the most profoundly round objects in the universe. When you look at the sun, or at distant stars twinkling across the night sky, you're witnessing nature's purest expression of equilibrium, an exquisite balance sculpted by gravity and pressure. These forces, locked in a constant struggle, shape stars into nearly perfect spheres. The roundness of a star isn't just a matter of appearance, it's a reflection of its inner harmony, a physical manifestation of the delicate balance that keeps it shining for billions of years. To understand why stars are so round, we need to go back to the very beginning of their lives, to the stellar nursery, where they are born from enormous clouds of gas and dust known as nebulae. These nebulae drift through space for millions of years, vast and diffuse, until something disturbs their calm. It could be a shock wave from a nearby supernova, a collision with another cloud, or even the gravitational influence of nearby stars. Once disturbed, gravity begins to pull the particles of gas, mostly hydrogen and helium, closer together. The more the gas contracts, the stronger the gravitational pull becomes, setting off a self-reinforcing collapse. As this material falls inward, it doesn't collapse into a flat shape, but into a spherical cloud. That's because gravity pulls equally from all directions toward the center of mass. Any irregularity, a bump here, a denser region there, gets evened out as matter moves inward. The only direction that gravity doesn't pull harder is along the radial line from the center. Everything else gets smoothed away. Over time, this contracting cloud becomes smaller, denser, and hotter. Eventually, at the very center, temperatures soar to millions of degrees, hot enough to ignite nuclear fusion. And that moment, the ignition of fusion, marks the birth of a true star. Fusion changes everything. While gravity continues to pull inward, trying to compress the star into an ever smaller sphere, fusion pushes back. Deep in the star's core, hydrogen atoms are forced together under immense pressure to form helium. This process releases staggering amounts of energy, which radiates outward as light and heat. That outward pressure, generated by the energy of fusion, perfectly counteracts gravity's inward pull. The result is hydrostatic equilibrium on a cosmic scale. The same balance we discussed earlier in planets, but vastly more powerful. In this state of balance, every layer of the star is stabilized by a precise distribution of forces. Gravity pulls material inward uniformly from all directions, and pressure from the hot gases and photons pushes outward equally in every direction. Because these forces act symmetrically, the star naturally assumes the most stable and efficient shape possible, a sphere. Any other form would be unstable. If a star were, for instance, elongated or lopsided, the areas with more curvature would experience stronger gravitational compression,
which would immediately redistribute mass until equilibrium and roundness was restored. This is why stars are so remarkably smooth and round, often more so than planets. On Earth, mountains rise and ocean trenches fall, distorting the surface by kilometers. But on the Sun, such deviations are minuscule, measured in mere tens of meters compared to its 1.4 million kilometer diameter. The Sun's surface is, for all practical purposes, smoother than a polished billiard ball. That's because its gaseous nature allows it to flow and settle into equilibrium continuously. Solid worlds can hold irregularities, gaseous ones cannot. Now, not all stars are perfectly spherical. Just like planets, stars rotate, and in some cases, they spin incredibly fast. This rotation causes the same phenomenon we see in planets, equatorial bulging. The faster a star spins, the more its equator bulges outward due to centrifugal force. Our own Sun rotates once every 27 days, which gives it a tiny but measurable equatorial bulge, only about 10 kilometers difference between the poles and equator, an incredibly small variation given its size. But some stars rotate so rapidly that their shapes are dramatically altered. For example, a Churnar, one of the brightest stars in the southern sky, spins at nearly 90% of its breakup speed, the speed at which it would begin to lose mass at the equator. As a result, its equatorial diameter is nearly 50% greater than its polar diameter. Instead of being perfectly round, a Churnar is distinctly oblate, resembling a flattened sphere. And yet even this distorted shape is a form of equilibrium, not the pure hydrostatic balance of a slow rotating star, but a rotational equilibrium, where gravity, pressure, and centrifugal force are all balanced in 3 dimensions.
It's fascinating to realize that despite such distortions, even the fastest spinning stars remain extremely close to spherical symmetry. Why? Because the forces that shape them are overwhelmingly central. Gravity's inward pull acts from the center outward, and the pressure of fusion pushes from that same point. These 2 forces define the geometry of stars. No matter how they rotate, vibrate, or evolve, the star's core remains the anchor, the point that ensures its shape is never far from round. This symmetry is also maintained over the star's life cycle. During its main sequence phase, the long, stable period when it steadily fuses hydrogen into helium, a star structure remains remarkably consistent. The balance of forces keeps it stable and round for billions of years. Only when fusion slows or stops does the balance falter. When hydrogen in the core runs out, the star begins to collapse under gravity's weight. The core heats up again, igniting new fusion reactions in outer layers, and the star expands into a red giant, a bloated, luminous sphere hundreds of times larger than before. Even in this inflated form, it retains its roundness, though now less uniform, with turbulent convection cells and flowing plasma shaping its surface. Eventually, after shedding its outer layers, the core that remains, a white dwarf, is once again almost perfectly spherical. Even at the smallest scales of stellar evolution, gravity's demand for symmetry reasserts itself. In more extreme cases where massive stars collapse beyond the white dwarf stage, the result is a neutron star or even a black hole, both of which push roundness to its ultimate limit. A black hole, in fact, is the purest sphere possible in nature, an object defined entirely by its mass and spin, its surface, the event horizon, a perfect mathematical sphere or spheroid. Stars then are more than luminous orbs of gas. They are cosmic laboratories where the laws of balance, symmetry, and energy find their most perfect expression. Gravity gathers matter inward, fusion pushes outward, and the 2 forces meet in a state of perpetual tension. The sphere that results isn't arbitrary, it's the natural outcome of physics searching for harmony. Even when we consider vast and violent stellar processes, solar flares, pulsations, eruptions, the underlying shape remains. A flare may distort a patch of plasma, but the global balance remains untouched. A star can pulsate, expanding and contracting rhythmically as it evolves, but always in spherical symmetry. It breathes, but it never loses its roundness. In the grand cosmic scale, stars embody the same principle that governs planets, raindrops, and even microscopic cells. Energy seeks balance. The roundness of stars is the visible signature of that balance, the physical form of peace between opposing forces.
In the next segment, we'll descend from the vastness of stars back to the tiny world of liquids, where a similar story unfolds on a much smaller scale. There, another kind of force, surface tension, plays the same role that gravity plays in the cosmos, shaping droplets into miniature world of perfect roundness. If stars are the grand symphonies of roundness in the cosmos, then liquid droplets are their miniature echoes here on Earth. From the vast scales of galaxies down to the tiniest drops of rain clinging to a leaf, nature repeats the same geometric truth. When forces act freely and evenly, the result is roundness. But in the world of liquids, the sculptor isn't gravity. It's something subtler and far more intimate, a force called surface tension. Surface tension is the invisible skin that coats every liquid. It's not a skin in the literal sense, but rather a manifestation of the molecular forces that hold the liquid together. To understand how it works, imagine the surface of a body of water. The molecules beneath the surface are surrounded on all sides by other water molecules. They experience equal attraction in every direction, so the net force on each one is zero. They're balanced. But the molecules at the surface are different. They have no neighbors above them, only beside and below. This imbalance means the surface molecules experience a net inward pull, as if the liquid were trying to shrink itself. That inward pull creates tension, hence the term surface tension. It's the liquid's way of minimizing its exposed surface area. Molecules on the surface rearrange themselves to make the surface as small as possible, because maintaining a surface costs energy. And what shape among all possible shapes has the smallest surface area for a given volume? The sphere. This is why when a droplet of water forms, it naturally becomes round. Whether it's a raindrop falling through a cloud, a bead of dew resting on grass, or a droplet floating in space, surface tension is constantly pulling the liquid molecules inward, forcing them into the most efficient, compact shape, a perfect sphere. This isn't just aesthetic, it's an expression of physics at its simplest. A spherical droplet minimizes surface energy, achieving equilibrium just as a planet or star does on a vastly larger scale. We can see this process in action every day, often without realizing it. When you watch raindrops form on a window pane, they start as tiny spheres. As they grow, they elongate slightly because gravity begins to act on them, stretching them downward. But in the absence of significant gravity, like in microgravity conditions aboard the International Space Station, liquid water behaves differently. Astronauts have demonstrated that in space, water doesn't spread or drip. It floats freely as perfect shimmering globes, miniature planets held together not by gravity, but by surface tension. The effect is mesmerizing, a vivid reminder that roundness is nature's universal signature, repeating itself even in the smallest scales.
To understand why liquids behave this way, it helps to consider the concept of energy minimization. Every physical system, from a raindrop to a galaxy, naturally tends to arrange itself in the lowest possible energy state. For a liquid, the highest energy region is the surface, where molecules are not fully surrounded by neighbors. The fewer surface molecules there are, the less total energy the system has. So, a liquid will always seek to reduce its surface area, and thus its energy, by becoming round. This principle is so fundamental that it appears across physics, chemistry, and biology alike. Different liquids have different levels of surface tension, depending on the strength of the forces between their molecules. Water, for example, has a relatively high surface tension because of hydrogen bonding, the strong attraction between its molecules. This is why small insects like water striders can walk across ponds without sinking. Their weight isn't enough to break the skin of tension at the surface. On the other hand, alcohol or oil with weaker molecular attractions have lower surface tension, so droplets of these liquids spread more easily and form flatter shapes. One of the most beautiful demonstrations of surface tension in motion is the way raindrops form and fall. In the atmosphere, water vapor condenses around tiny particles of dust or salt, forming droplets. At first, these droplets are perfectly spherical, shaped by surface tension alone. But as they fall through the air, they encounter resistance. Air pressure pushes against their bottoms, flattening them slightly. Contrary to popular depictions, raindrops don't look like teardrops. They're closer to the shape of hamburger buns, round on top and flatter underneath. Still, if you could momentarily freeze them in midair, you'd see their natural tendency to roundness, always striving toward equilibrium, even as external forces act upon them.
Surface tension also explains why small droplets merge so eagerly when they touch. Two tiny spheres of liquid have more surface area than a single larger sphere of the same total volume. When they merge, the new droplet has less surface area and therefore less energy. That's why water droplets on a window seem to chase each other. They're driven by the physics of energy minimization, just like collapsing stars or coalescing planets. The scale is different, but the principle is identical. In more controlled environments, we can observe this behavior even more clearly. Scientists use high-speed cameras to capture how droplets of different liquids behave when they collide. Some bounce, some merge instantly, and some oscillate before settling into a perfect sphere again. Each movement is a dance of forces, cohesion pulling molecules inward, inertia stretching them outward, and surface tension restoring balance. The moment the droplet stabilizes, it always returns to the same iconic shape, round. This phenomenon isn't limited to water. Lava droplets cooling in midair, molten metal in microgravity experiments, and even droplets of oil suspended in another fluid all display the same tendency. The driving force changes. Sometimes it's surface tension, sometimes it's a mix of molecular attraction and buoyancy. But the outcome remains constant. When no external constraint interferes, liquids become spheres. There's something deeply poetic about this universality. A raindrop forming in a storm cloud and a planet forming in a dust cloud obey the same fundamental logic. Both are shaped by the interplay of inward and outward forces seeking equilibrium. Both find stability in symmetry. Both settle into the same geometry, the sphere. And yet, while the physics are the same, the scale changes everything. In the realm of liquids, surface tension is dominant, while gravity is negligible. On the scale of planets and stars, the roles are reversed. Gravity becomes the sculptor, and internal pressure the counterforce. But both systems speak the same language of energy minimization and balance. This connection between surface tension and gravity, between the microscopic and the cosmic, is one of the most elegant symmetries in physics. It reminds us that the universe doesn't have one set of rules for small things and another for large things. It's a continuous spectrum of the same principles expressed at different magnitudes. So the next time you watch a raindrop slide down a window or see a bead of water resting on a leaf, realize that you're witnessing the same principle that shapes planets, stars, and galaxies. The droplet's roundness isn't trivial. It's the universe whispering the same ancient truth it speaks through every sun and every world. Balance creates beauty, and beauty seeks roundness. As we move deeper into this journey, we'll explore this fascinating connection more explicitly, how surface tension on the smallest scales mirrors gravity on the largest, both acting as invisible sculptors of symmetry throughout nature.
At first glance, surface tension and gravity couldn't seem more different. One governs the delicate behavior of liquid droplets, the other dictates the motion of planets and the fate of stars. One operates quietly at the scale of molecules, the other dominates entire galaxies. Yet, when we look closely, when we strip away the differences in scale and focus on the underlying principles, we find something astonishing. Surface tension and gravity are two expressions of the same universal tendency toward balance, symmetry, and energy minimization. They are the twin sculptors of roundness, one ruling the microscopic, the other commanding the cosmic. Both surface tension and gravity act as centralizing forces. They pull matter inward toward a center, working to minimize energy and create stability. In the case of a liquid droplet, the cohesive attraction between molecules at the surface pulls the liquid into the smallest possible surface area, a sphere. In the case of a planet or star, gravity pulls every particle toward the center of mass, distributing material uniformly until the body becomes spherical. Despite their different origins, both forces produce the same outcome, a state of equilibrium where inward and outward pressures balance perfectly. Let's visualize the comparison. Imagine a droplet of water suspended in space, free from any outside interference. The molecules at its surface pull inward because they lack neighbors above them. This inward pull compresses the droplet equally in all directions, and as a result, the droplet becomes round. Now imagine a planet forming in the vacuum of space.
Dust, ice, and rock begin to clump together under neutral gravity. As more mass accumulates, the gravitational pull strengthens, drawing material inward toward the center. Over time, the irregular shapes moves out until gravity has pulled everything into the most stable, symmetrical shape possible. Again, a sphere. In both cases, the forces act to minimize potential energy. For a liquid droplet, the energy cost comes from the surface, the boundary between the liquid and its surroundings. A smaller surface area means fewer surface molecules and therefore lower energy. For a planet, the energy cost is gravitational potential energy, the energy stored in the mutual attraction between all its particles. A spherical distribution minimizes that energy because it brings mass as close as possible to the center. The mathematics describing these two systems even share similar forms. Both involve finding the lowest energy configuration of matter under the influence of an inward acting force. Another profound similarity is how both forces respond to disturbances. If you disturb the surface of a water droplet, say by tapping it or blowing air across it, ripples form and travel outward. But almost immediately, surface tension acts to restore the droplet to its original spherical shape. The same is true for celestial bodies. When a meteor strikes a planet or a gravitational wave distorts a star, gravity pulls the material back toward equilibrium, smoothing out the disruption over time. Both systems heal themselves, erasing irregularities as they seek their natural, balanced state. Even in their differences, the parallels are remarkable. Surface tension arises from the electromagnetic forces between molecules, a short-range interaction that only operates across nanometers. Gravity, on the other hand, is a long-range force that acts across the universe. But both are collective forces, meaning they emerge not from the behavior of a single particle, but from the combined behavior of many. No single water molecule has surface tension on its own. It's the cooperation of trillions of them that creates it. Similarly, a single dust grain has negligible gravity, but when billions of them gather, their collective attraction grows strong enough to mold worlds. In both cases, roundness is not imposed from outside, it emerges from within, as the natural consequence of countless interactions balancing out. We can also see this connection in how both forces scale with size. For tiny droplets, surface tension dominates because molecular forces are strong compared to the droplet's weight. That's why you can have a perfectly round bead of water resting on a surface or floating in air. Gravity is too weak at that scale to distort it. But as the droplet grows larger, gravity begins to take over. Beyond the few millimeters, the droplet starts to flatten under its own weight, because surface tension can no longer fully counteract gravity's pull. This crossover point, where surface tension yields to gravity, is a fascinating bridge between the two regimes. It shows how seamlessly nature transitions from the microscopic to the macroscopic, with the same principles governing both, just expressed through different forces. This balance is even mirrored in experiments conducted in microgravity. On the International Space Station, where gravity is nearly absent, water behaves as if surface tension were the only force left active. Astronauts have released blobs of water that float freely, holding their spherical shape perfectly. These floating spheres of liquid are, in essence, miniature planets held together not by gravity, but by surface tension acting as molecular gravity. Each molecule pulls its neighbors inward, just as each atom of rock or gas does in a planet, creating an identical geometry for entirely different reasons.
In fact, the mathematics of equilibrium for both systems are deeply related. Physicists describe the shape of a droplet or a planet using equations that balance inward and outward forces. For droplets, this is expressed through the Young-Laplace equation, which relates the pressure difference across a curved surface to its surface tension and curvature. For planets and stars, the equivalent concept is hydrostatic equilibrium, which balances gravitational pressure with internal pressure. Both equations describe the same fundamental concept. A stable, rounded shape emerges when all forces are equal in every direction. The beauty of this parallel lies in how it unites the very small with the unimaginably large. The same principle that gives us a raindrop is the one that gives us a star. Both are products of the universe's drive towards symmetry and efficiency. Both seek the lowest energy state available to them, and both achieve it through roundness, a shape that is as simple as it is profound. There's also a poetic continuity between the two. The water in that raindrop once existed as vapor, perhaps evaporated from the ocean, and long before that, the atoms within it were born in the heart of a star. Those atoms were forged through nuclear fusion, the same process that made the star round in the first place. Billions of years later, those same atoms participate in a new act of symmetry, forming a droplet that mirrors the star's shape on an infinitely smaller scale. It's a cosmic echo, a repetition of form across time and size, showing that nature's geometry never forgets itself. So whether it's the cohesive skin of a droplet or the gravitational pull of a planet, both forces tell the same story. The universe abhors imbalance. It pulls inward until all directions are equal, until energy is minimized, until chaos gives way to order. Roundness, then, is not just a shape, it's a signature of equilibrium written into the laws of nature. In the next segment, we'll journey even smaller, into the microscopic world, where cells, bubbles, and even molecules reveal the same astonishing tendency. There, we'll see how energy minimization continues to guide form, shaping the very foundations of life and matter in ways that mirror the curvature of worlds and stars. When we descend from the cosmic scale of planets and stars to the microscopic realm, a world invisible to the naked eye, yet brimming with complexity, we find that roundness persists. It's astonishing to realize that the same geometric principle shaping galaxies also appears in the tiniest drops of matter and life itself. The tendency towards spherical form is not limited by size or distance. It's a universal pattern driven by one unifying law of nature: energy minimization. Wherever forces are free to act evenly and efficiently, matter curves inward towards symmetry. Whether it's a soap bubble floating through the air, a red blood cell drifting through the bloodstream, or a microscopic oil droplet suspended in water, roundness reemerges, elegant, inevitable, and purposeful. At the microscopic level, the dominant forces change. Gravity, the master of the cosmic stage, becomes almost irrelevant here. Its influence is so weak that it's overshadowed by electromagnetic forces, molecular motion, and chemical interactions. Instead, surface tension, internal pressure, and intermolecular attraction take center stage. These forces, though minuscule, obey the same logic. Systems tend to minimize potential energy, and in doing so, they assume the most efficient possible configuration, the sphere. Consider the soap bubble, one of nature's simplest yet most perfect expressions of this principle. When you blow a bubble, you trap a thin film of soapy water around a pocket of air. The molecules in that film, water molecules surrounded by soap molecules, are all tugging on one another, trying to contract and reduce the total surface area. The pressure inside the bubble pushes outward and surface tension pulls inward, until a perfect balance is achieved. That balance naturally forms a sphere, because a sphere encloses the maximum volume with the minimum surface area. If the bubble were any other shape, say a cube or a cylinder, it would have more surface area for the same volume, which means higher surface energy. The sphere is nature's way of economizing. Soap bubbles are a particularly vivid example of energy minimization in action. When multiple bubbles touch, they merge and rearrange their surfaces into geometric patterns that minimize total surface area across the group. The angles at which the films meet, the curvature of each surface, all are dictated by the physics of minimal energy. This same mathematics, known as the Young-Laplace equation in physics, also governs the shapes of liquid droplets, biological membranes, and even some cellular structures. In all these systems, surface tension acts as a balancing force, constantly reshaping matter towards smooth, rounded forms.
Now let's look at the cell, the fundamental unit of life. Many cells, especially in their simplest form, such as bacteria, protozoa, and certain animal cells, are approximately spherical. Why? Because a spherical shape minimizes the surface area for a given volume, just like a droplet or a bubble. This efficiency is crucial for living systems, which must regulate the exchange of nutrients and waste through their membranes. A sphere offers the optimal ratio of surface area to volume for conserving energy and maintaining stability. Cells that need more surface for interaction evolve into other shapes, but the sphere remains the baseline, the natural, energetically favorable starting point of life's geometry. Even the membranes of cells and organelles obey this rule. The lipid bilayer that makes up a cell's membrane behaves much like a liquid film, flexible and dynamic. The molecules that form it, amphiphilic lipids with hydrophilic heads and hydrophobic tails, naturally assemble into spherical structures called micelles or liposomes when placed in water. This spontaneous organization minimizes the system's free energy, protecting the hydrophobic tails from water exposure while maximizing the stability of the entire structure. In essence, the molecular drive toward roundness is the foundation of biological organization itself. Even organelles inside cells, such as vesicles and the nuclei, tend toward spherical shapes when free from mechanical constraints. Vesicles, tiny sacs that transport materials within the cell, are perfect microscopic examples of this principle. They form when sections of the cell membrane pinch off, enclosing small pockets of fluid. Surface tension and membrane elasticity then reshape them into spheres, because that's the configuration that minimizes energy. These vesicles are like biological soap bubbles, carrying essential materials through the microscopic cosmos of the cell. Moving down another scale, we find that some molecules themselves exhibit spherical symmetry. Atoms, for instance, are often modeled as spheres because the probability distribution of their electrons, the regions where electrons are most likely to be found, is symmetrical around the nucleus. Especially in the simplest atom, hydrogen, the electron cloud forms a perfect sphere of probability. Larger molecules, too, sometimes adopt spherical or near-spherical shapes when such forms minimize their potential energy. A striking example is the family of carbon molecules known as fullerenes or buckyballs. These are hollow, spherical cages of carbon atoms arranged like the panels of a soccer ball. The structure is remarkably stable, precisely because its shape distributes internal stress evenly, a molecular expression of the same geometry that shapes planets and droplets. Another stunning example lies in the microscopic architecture of viruses. Many viruses, such as the poliovirus or the adenovirus, are encased in roughly spherical shells made up of repeating protein subunits. This design, called an icosahedral structure, is nature's way of building the most stable enclosure from identical components. The icosahedron, though faceted, approximates a sphere and allows the virus to use the fewest possible types of proteins to create a strong, compact, and symmetrical shell. Here again, the principle is efficiency. The virus minimizes the energy required for self-assembly while maximizing structural integrity. It's humbling to realize that from soap films to viral shells, from vesicles to molecular clusters, the same fundamental rule applies. Systems naturally seek the configuration of least energy, and that configuration is almost always round. The smoothness and symmetry of a sphere represent balance. Every point on its surface is equidistant from the center, every direction equal. No other shape embodies such perfect neutrality. Even in dynamic systems where motion and energy flow constantly, roundness appears again and again. Consider a droplet of oil suspended in water under a microscope. It may wobble, stretch, and deform, but once the forces settle, it returns to a sphere. The same thing happens when tiny bubbles of gas rise through a liquid. Turbulence may distort them temporarily, but surface tension always restores their roundness. Nature's constant preference for symmetry ensures that over time, disorder resolves into equilibrium, and equilibrium manifests as smooth curvature. In the microscopic world, then, roundness is not just common, it's fundamental. It emerges from the molecular interactions that govern everything from chemistry to biology. It's the geometry of stability, efficiency, and harmony. Just as gravity gives large bodies their rounded form, the cohesive forces of molecules give the same form to small ones. Both realms, the cosmic and the microscopic, obey the same deep rule. Minimize energy and you will find the sphere. In the next segment, we'll explore this principle in its most universal form, energy minimization itself, and uncover why nature is always striving towards simplicity, efficiency, and balance. From the smallest droplet to the largest galaxy, the universe's drive to reduce energy is what sculpts roundness across every scale. At the heart of everything we've talked about so far, from droplets to planets, from soap bubbles to stars, lies one unshakable truth of the universe. Nature always seeks to minimize energy. This principle isn't just a convenient pattern or a reoccurring theme. It's one of the deepest, most fundamental laws of physics. Every atom, every molecule, every celestial body follows this quiet commandment written into the fabric of existence. Find the state of least resistance, the state of balance, the state of lowest possible energy.
Energy minimization is the universe's way of finding order amidst chaos. When we look at the cosmos, it's easy to see grandeur, massive stars, swirling galaxies, erupting volcanoes. But beneath all that motion, there's a kind of serene logic guiding everything. Systems naturally evolve toward equilibrium, the point where competing forces cancel each other out. It's not just a physical tendency, it's a kind of cosmic efficiency. Nothing in nature wastes effort. Every structure, every form, is a product of forces arranging matter into the configuration that requires the least energy to maintain. So why does this drive toward minimal energy create roundness? To answer that, we have to look at what low energy really means. Energy in physics can take many forms: gravitational, kinetic, thermal, chemical. But in all cases, minimizing it means reducing imbalances. Forces like gravity, surface tension, and pressure act to redistribute matter until no direction has an advantage over another. The only shape that perfectly satisfies that condition, where all points on the surface are equidistant from the center, is a sphere. In a sphere, there are no corners, no edges, no privileged directions. Every part is equally balanced, every force equally opposed. It's the physical embodiment of harmony. Take gravity, for example. When a cloud of gas and dust begins collapsing under its own gravity, every particle is attracted toward the center. The collapse continues until the inward gravitational pull is balanced by outward pressure from heat, radiation, or rotation. That balance point, hydrostatic equilibrium, forms a sphere because it's the configuration where the energy of the system is minimized. Any other shape would require extra energy to sustain uneven forces. The sphere, therefore, is not just a random shape. It's gravity's most efficient solution to its own problem. On a completely different scale, surface tension behaves the same way. A droplet of liquid becomes round because that shape minimizes its surface area for a given volume, and therefore minimizes the potential energy stored in its surface. Nature doesn't choose a sphere. It simply settles into it because every other shape would require extra energy to maintain. You can think of this as nature's version of laziness, or more accurately, its path of least action. In physics, this concept is formalized as the principle of least action, which states that the path taken by a system between two states is the one that minimizes the total action, a measure related to energy and time. In simpler terms, the universe always takes the most efficient route possible. Roundness, then, is a direct visual expression of that efficiency. When you see a raindrop, a bubble, a planet, or a star, you're seeing nature's way of saying, this is the simplest, most stable form I can take. Round shapes minimize surface area, minimize gravitational potential energy, and minimize internal stresses. They require no unnecessary complexity to maintain themselves. That's why, when left undisturbed, matter tends to roundness. It's the geometry of rest, the geometry of peace. But this principle doesn't stop at physical structures. It's deeply embedded in the mathematics that governs everything. The equations of thermodynamics, for instance, describe how systems evolve towards states of minimum free energy. The second law of thermodynamics tells us that entropy, or disorder, increases over time.
but it's often misunderstood as meaning things fall apart. In reality, systems are not collapsing into chaos. They're relaxing into equilibrium. They're finding the state where no more work can be extracted, where energy is evenly distributed. A sphere, as a geometric expression of equilibrium, reflects that very same logic. It's uniform, balanced, and stable. We see this principle even in the biological world. A cell, as we've discussed, often forms a spherical shape because that's the lowest energy configuration for a membrane enclosing fluid. When a cell divides, it elongates and stretches, but after the division, both daughter cells tend to return to round forms. Even in tissue growth, surface tension and internal pressure compete, guiding cells to pack together efficiently, often into near-spherical or polyhedral arrangements. Nature's architecture is a perpetual compromise between minimizing energy and maximizing function. Another fascinating example lies in bubbles and foams. When multiple bubbles come into contact, they rearrange themselves into shapes that minimize total surface area, even when that means sacrificing perfect spheres. The mathematics behind these shapes, studied in the field of minimal surface geometry, reveal a remarkable truth. Even when the environment is complex, nature still finds the shape that requires the least energy to exist. This is why honeycombs, for instance, form hexagonal cells. The hexagon, while not spherical, is the most efficient way to pack space with equal-sized units. Roundness gives way to hexagonal symmetry when the goal shifts from enclosing space efficiently to filling it efficiently, but the guiding principle, energy minimization, remains the same. On a completely different scale, atomic and molecular levels, energy minimization governs bond angles, molecular geometry, and crystal structures. Atoms arrange themselves in configurations that balance attractive and repulsive forces. The electron clouds around nuclei often adopt symmetrical shapes because symmetry distributes charge evenly, minimizing potential energy. This is why spherical harmonics, mathematical functions describing these distributions, are so central to quantum mechanics. Even at the subatomic scale, roundness emerges as the language of stability. What's profoundly beautiful about this principle is its universality. It doesn't matter what forces are involved: gravitational, electromagnetic, nuclear, or mechanical. They all share this same tendency. Systems evolve towards simplicity because simplicity costs less energy to maintain. Complexity exists, of course, but it's often transient, dynamic, or driven by external inputs of energy. Left alone long enough, every system calms into balance, and balance manifests as symmetry.
This universal drive has even philosophical implications. If you zoom out far enough, the entire universe itself appears to be obeying an energy minimization principle. The expansion of space, the formation of galaxies, the cooling of stars, all are processes leading the cosmos toward lower and lower energy states. Entropy increases, temperatures drop, structures stabilize. Even in this grand cosmic evolution, the same rule that shapes a soap bubble is at work, expressed across billions of light years. Roundness, therefore, is not merely a shape, it's a statement. It's nature's way of revealing its preference for balance over chaos, simplicity over complexity, and efficiency over waste. Every sphere, from an atom to a star, is a silent testament to the universe's relentless pursuit of equilibrium. It's a reminder that even in a universe filled with motion and change, there exists an underlying drive towards stillness, a gravitational and energetic serenity that gives birth to harmony and form. And yet, not everything in the universe is perfectly round. Forces sometimes compete, dynamics shift, and balance can be disturbed. In the next segment, we'll explore these exceptions to roundness, the cosmic irregularities, distortions, and imperfections that reveal how rotation, collisions, and external influences can stretch or twist nature's most perfect shape, reminding us that even symmetry has its limits in an active, evolving universe. While roundness is nature's favored shape, it isn't absolute. The universe, as much as it strives for equilibrium, is also a place of constant motion, turbulence, and conflict.
forces don't always act in perfect harmony. And when they clash, roundness begins to falter. The result is a fascinating variety of imperfect spheres, stretched moons, flattened planets, and even lopsided stars, each shaped by competing influences that twist nature's smooth geometry into something more complex. These exceptions to roundness reveal just how dynamic the universe truly is. They remind us that while roundness is the goal of balance, the cosmos rarely sits still long enough to stay perfectly balanced. The first and perhaps most common cause of deviation from roundness is rotation. When an object spins, centrifugal force, the apparent outward push experienced by rotating matter, acts against gravity. This force is strongest at the equator, where rotation speed is highest, and weakest at the poles, where rotation speed drops to zero. As a result, a spinning sphere bulges outward at its middle and flattens slightly at its poles. The shape that emerges is called an oblate spheroid, still roughly spherical but subtly squashed. Earth itself is one of the best examples of this phenomenon. Though we often call it round, our planet is technically an oblate spheroid. Due to its rotation, Earth's equatorial diameter is about 43 kilometers, or 27 miles, greater than its polar diameter. That might not sound like much compared to its overall size, but it's enough to slightly affect gravity and even how we measure sea level. You weigh a bit less at the equator than at the poles, not because gravity weakens dramatically, but because the outward centrifugal force from Earth's spin counteracts it ever so slightly. The effect becomes even more pronounced in gas giants like Jupiter and Saturn. These massive planets rotate incredibly fast. Jupiter completes a full rotation in just about 10 hours. The result is a visibly flattened shape. Jupiter's equatorial diameter is roughly 10,000 kilometers larger than its polar diameter. When we look at images of Jupiter from space, we can clearly see this bulge, a reminder that even the mightiest gravitational forces must contend with motion's influence. Saturn, rotating almost as rapidly and composed mostly of hydrogen and helium, shows an even more dramatic flattening. These planets are round in spirit, but their rapid spins leave a permanent, graceful distortion, a dynamic compromise between balance and momentum. Rotation, however, isn't the only force that disrupts roundness. Tidal forces, the stretching caused by gravitational interactions between celestial bodies, can twist once spherical objects into elongated or even tear-shaped forms. When one body orbits another, the near side experiences a stronger gravitational pull than the far side. This differential force stretches the object along the line connecting the two bodies, creating a tidal bulge. Earth experiences this constantly due to the moon's gravitational pull, which causes our ocean tides. But in more extreme cases, like moons orbiting close to their planets, the effects can be far more dramatic. One famous example is Jupiter's moon Io. Locked in a gravitational tug-of-war between Jupiter and neighboring moons, Io is stretched and squeezed so intensely that its interior remains molten, driving constant volcanic activity. The moon itself is not a perfect sphere. It's slightly elongated along the direction facing Jupiter, a constant victim of the immense tidal forces that churn it from within. An even more extreme case occurs when an object gets too close to a larger body, approaching what's known as the Roche limit. Within this distance, tidal forces become so strong that they can overcome an object's self-gravity, pulling it apart entirely. This is believed to have been what happened to the material forming Saturn's rings, remnants of a moon or comet that ventured too close and was torn apart. Before destruction, however, such an object would have been stretched into a long, thin, oval shape, the ultimate distortion of roundness under gravitational stress. Collisions also play a major role in breaking perfect symmetry. The early solar system was a violent place, with countless planetesimals, the building blocks of planets, colliding, merging, or shattering. Even today, impacts continue to sculpt the surfaces of planets, moons, and asteroids. A single large collision can alter a body's rotation, shape, and even its internal structure. Scientists believe our moon was formed when a Mars-sized object named Theia collided with the young Earth about 4.5 billion years ago. That colossal impact not only birthed the moon, but also likely contributed to Earth's axial tilt and oblate shape. Other moons and asteroids bear the scars of similar violence. The asteroid Vesta, for instance, is roughly spherical, but has a massive crater that makes it distinctly asymmetrical. The smaller the object, the more susceptible it is to such distortions because its gravity isn't strong enough to pull it back into shape afterward. Phobos, one of Mars's moons, looks more like a lumpy potato than a sphere, a relic of uneven formation and bombardment. Gravity tries to smooth it out, but there simply isn't enough mass to succeed. Even stars, those glowing spheres of plasma that seem so perfectly round from a distance, can betray subtle imperfections. Rapidly spinning stars can become oblate, just like planets. The star Altair, for example, rotates so fast that it bulges noticeably at its equator. Other stars can be distorted by tidal forces if they orbit close companions, forming binary systems where each star pulls the other slightly out of shape. In extreme cases, these stars can share material, forming pear-shaped or even dumbbell-like structures, as gravity and rotation wage an endless tug-of-war.
Beyond physical forces, magnetic fields and differential heating can also cause asymmetries. On Earth, the equatorial bulge is accompanied by slight variations in density and composition, the result of geological processes and magnetic influences. In stars, uneven heating caused by magnetic activity can create bulges or depressions on their surfaces, leading to non-uniform shapes when viewed up close. These imperfections are fleeting, often shifting and smoothing out over time, but they reveal that roundness is rarely perfect in a universe of constant motion. In all these exceptions, from flattened planets to stretched moons and cratered asteroids, there's a deeper truth. Imperfection doesn't defy the rule of roundness, it refines it. These deviations show us how roundness emerges as a balance among many forces, not as an absolute law, but as an equilibrium state that can shift with circumstances. A spinning planet is still round, but its shape tells the story of its rotation. A tidally distorted moon is still rounded, but its elongation speaks of the gravitational struggles it endures. Even a lumpy asteroid, irregular as it may seem, hints at a fundamental truth. If only it were larger, its own gravity would have smoothed it into a sphere. The imperfections, then, are not contradictions of the rule, but variations of it. They reveal the dynamic interplay between forces that shape matter across scales. Roundness, in the end, is not a static state, but a living conversation between competing influences, between gravity's inward pull, motion's outward push, and the eternal balancing act of energy. In the next segment, we'll dive deeper into one of the most fascinating distortions of all, rotational flattening. How spinning worlds and stars become oblate spheroids, and why this subtle deformation tells us so much about the physics of motion and mass in the universe. Rotation, the graceful spin that gives planets their days and nights, is one of the most beautiful yet disruptive forces in the cosmos. It introduces rhythm into stillness, motion into equilibrium, and in doing so, it slightly bends one of nature's most perfect shapes. When a celestial body begins to rotate, its own inertia pushes back against the uniform inward pull of gravity. The result isn't a perfect sphere anymore, but something subtly and sometimes dramatically distorted. This phenomenon is known as rotational flattening, and it's what gives rise to the oblate spheroid, a shape that is wider at the equator and narrower at the poles. It is one of the universe's most elegant compromises, the balance between symmetry and spin. To understand why rotation flattens celestial bodies, we have to start with the forces at play. A planet, moon, or star in motion experiences centrifugal force, an apparent outward force that acts perpendicular to the axis of rotation. This force doesn't actually push objects away, rather it arises from inertia, the tendency of matter to move in a straight line. As a rotating planet spins, every particle at its surface tries to continue moving straight, but gravity constantly pulls it toward the center. The faster the rotation, the stronger this outward tendency becomes. At the equator, where the surface is moving fastest, the centrifugal effect is greatest. At the poles, where the surface barely moves, it's weakest. This imbalance means gravity effectively acts slightly weaker at the equator than at the poles. Over time, the planet adjusts its shape to reflect this distribution of forces. It bulges outward around the equator and flattens slightly at the poles until equilibrium is restored.
The resulting shape, the oblate spheroid, is the natural form of a rotating, self-gravitating body. Even Earth, often depicted as perfectly round, isn't immune to this effect. Our planet spins once every 23 hours and 56 minutes, fast enough to create a measurable equatorial bulge. Earth's equatorial radius is about 6,378 kilometers, while its polar radius is about 6,357 kilometers, a difference of roughly 21 kilometers. That means if you could shrink the Earth down to the size of a basketball, the bulge would only be about the thickness of a credit card. Yet it's enough to slightly influence gravity, satellite orbits, and ocean tides. The planet's shape reflects its motion. It is round, yes, but not motionlessly so. It's a dynamic equilibrium between gravity's inward pull and rotation's outward push. The faster an object spins, the more pronounced this flattening becomes. In the solar system, the most striking examples of rotational flattening are found among the gas giants, Jupiter and Saturn. These massive worlds rotate incredibly quickly relative to their size. Jupiter completes a full spin in just about 10 hours, while Saturn takes roughly 10.7 hours. Given their enormous diameters, more than 10 times that of Earth, their equatorial regions are moving at breathtaking speeds. The centrifugal effect is so strong that both planets bulge noticeably. Jupiter's equatorial diameter is about 9,275 kilometers greater than its polar diameter. Saturn's distortion is even more extreme. Its equatorial diameter exceeds its polar one by nearly 10%. If you could observe Saturn closely, you'd see that its flattened poles make it look almost squashed, like someone gently pressed down on the top and bottom of a perfect sphere. This shape isn't just aesthetic, it has deep implications for its internal structure. The amount of flattening gives scientists clues about how mass is distributed within. For example, Saturn's greater oblateness compared to Jupiter suggests that its mass is spread out, consistent with the fact that Saturn has a lower overall density. It's less compact, more fluid, and more easily deformed by its rotation.
Rotational flattening also reveals how the composition of a planet or star affects its ability to deform. Gas giants, being mostly made of hydrogen and helium, have very little structural rigidity. They can shift and bulge with relative ease, allowing rotation to shape them dramatically. In contrast, rocky planets like Earth or Mars are more rigid. Their solid crusts resist deformation, so their flattening is far less pronounced. The same rule applies to stars. A dense, compact star like the Sun has only a slight equatorial bulge because its rotation period is relatively slow, about 25 days at the equator. But stars that spin much faster exhibit noticeable flattening. One of the most fascinating examples of this is the star Altair, located about 16.7 light-years away in the constellation Aquila. Altair rotates once every 9 hours, nearly 100 times faster than the Sun. Because of this incredible speed, it's about 20% wider at its equator than at its poles. Observations from interferometric telescopes have even confirmed this flattening visually, making Altair one of the first stars whose oblate shape was directly measured. Other stars, like Achernar, spin even faster, reaching a point where the equatorial bulge becomes so pronounced that they risk shedding material from their outer layers. These rapidly rotating stars illustrate how extreme rotation can push matter to its limits. Gravity still holds them together, but only just. On an even grander scale, rotational flattening plays a key role in the formation and behavior of galaxies. Spiral galaxies, including our Milky Way, are essentially vast oblate structures on a cosmic scale. They form disks rather than spheres because the rotation of billions of stars within them creates an overall flattening effect. In this case, gravity tries to pull everything inward, while angular momentum, the rotational equivalent of inertia, keeps the system spread out in a plane. The balance of these forces results in the breathtaking spiral shapes we see through telescopes. The same physical law that flattens Saturn's poles also sculpts entire galaxies, proving once again that scale doesn't change the underlying logic of nature. Rotational flattening doesn't just alter shape. It influences gravity, weather, and even magnetic fields. On Earth, for example, the equatorial bulge affects how satellites orbit, causing their paths to precess slightly over time. On Jupiter and Saturn, the bulges play a role in the planet's strong magnetic fields, helping shape their auroras and radiation belts. The flattening also affects how energy is distributed within these planets, contributing to the formation of powerful equatorial jet streams and banded cloud patterns, visible signatures of the ongoing dance between rotation and equilibrium. At the heart of all this is a simple but profound truth. Rotation creates resistance to perfect symmetry. The faster an object spins, the more it fights against the pull of its own gravity. But even this resistance is orderly. It doesn't shatter the symmetry, it reshapes it. The result, the oblate spheroid, is itself a kind of compromise between motion and stillness. It's nature saying, I will stay round, but I must also move. Rotational flattening therefore stands as one of the universe's most graceful demonstrations of balance in action. It shows us that roundness is not fragile. It can bend, adapt, and survive even in motion. The flattened poles of planets and stars are not imperfections. They are signatures of vitality, proof that equilibrium can coexist with dynamism. Yet rotation is not the only external factor capable of bending roundness. Other forces, particularly tidal interactions, can stretch, twist, and distort celestial bodies far more dramatically, turning spheres into elongated shapes and, in some cases, tearing them apart. In the next segment, we'll explore how external forces, from gravitational tugs to magnetic stresses, deform the universe's most perfect shape and create the cosmic asymmetries that make every world unique. When we think of celestial bodies like planets and moons, it's tempting to imagine them as self-contained worlds, sculpted solely by their own gravity and motion. Yet the universe is not a place of isolation. It's a vast web of relationships where every object feels the pull of others around it. External forces, especially tidal forces, can profoundly reshape these worlds, pulling them away from perfect roundness and leaving behind visible marks of their cosmic interactions. In this way, even the most spherical bodies are subtly, or sometimes dramatically, deformed by the invisible hands of gravity from their neighbors. To grasp how this works, we first need to understand what a tidal force truly is. In essence, tides arise because gravity is not uniform across a body. The side closer to a massive neighbor experiences a stronger gravitational pull than the far side. This difference stretches the object along the axis connecting the two bodies. If Earth and the Moon were rigid, featureless spheres, this tug-of-war would still create an internal strain. But since they both have some flexibility, whether in their oceans, crust, or internal layers, this stretching manifests as tidal bulges. We witness this every day on Earth in the rise and fall of our ocean tides. The Moon's gravitational pull draws ocean water slightly towards it, creating a bulge on the side facing the Moon. At the same time, the opposite side of the planet experiences a bulge as well, caused by inertia, as the Earth-Moon system revolves around the shared center of mass. As the Earth rotates, these bulges appear to move around the planet, giving us two high tides and two low tides roughly every 24 hours. It's an elegant dance, one that visibly demonstrates how an external gravitational influence can deform even a massive body like Earth, if only slightly. But tidal forces don't just move oceans. They can stretch rock, reshape orbits, and even generate heat. One of the most extreme examples of tidal deformation in our solar system is Io, Jupiter's innermost large moon. Locked in a gravitational tug-of-war between Jupiter and the other Galilean moons, Europa and Ganymede, Io is constantly squeezed and stretched as it orbits. This relentless flexing generates immense internal friction, melting much of its interior, and powering hundreds of active volcanoes, making Io the most volcanically active body in the solar system. Its surface is scarred and molten, and its shape deviates slightly from a perfect sphere due to these ongoing stresses.
The same principle applies to Europa, another of Jupiter's moons, though in a more subtle way. Beneath its icy surface lies a global ocean of liquid water, kept from freezing by the tidal flexing induced by Jupiter's gravity. The cracks and streaks we see on Europa's surface, called lineae, are direct evidence of this deformation. They mark areas where the moon's crust has been pulled apart and shifted due to varying tidal stress. Here, tidal forces not only shape the moon's geometry, but also sustain its internal energy, perhaps even creating conditions suitable for life. A similar story unfolds around Saturn with its moon Enceladus. Like Europa, Enceladus experiences intense tidal stretching, which heats its interior and fuels the spectacular geysers that erupt from its south pole, ejecting plumes of water vapor and ice into space. This tidal activity also slightly distorts the moon's shape, revealing how gravitational interaction can simultaneously shape, warm, and sustain a celestial body. Tidal deformation isn't limited to moons. It also affects planets. Take Earth again. While the moon causes oceanic tides, the sun exerts its own tidal pull, though weaker due to its greater distance. The combined effects of solar and lunar tides can sometimes amplify or cancel each other, leading to spring or neap tides. But in more extreme systems, such as close binary star pairs, these gravitational interactions can drastically reshape stars themselves. In a close binary system, where two stars orbit each other at short distances, the mutual tidal forces can stretch each star into an elongated, almost egg-like shape. Over time, these distortions can synchronize their rotations, a process called tidal locking, where each star always shows the same face to the other, just as the moon does to Earth. In some cases, the gravitational pull can be so strong that the outer layers of one star flow toward the other, creating a Roche lobe, a teardrop-shaped region around each star, marking the limit of its gravitational influence. If one star fills its Roche lobe, it begins to lose material to its partner, forming dramatic accretion disks, and even leading to nova explosions. This concept of the Roche limit defines the point at which tidal forces overpower a body's self-gravity, tearing it apart entirely. We see the evidence of this in Saturn's rings, which are believed to be the remnants of a shattered moon or comet that wandered too close to the planet. Inside the Roche limit, an object cannot remain intact. Gravity from the larger body pulls harder on its near side than its far side, effectively ripping it apart. The countless particles that now make up Saturn's magnificent rings each orbit independently, collectively tracing a flattened but circular pattern around the planet. Here, roundness reappears in a new form, not as a solid sphere, but as a ring of symmetry born from destruction. Tidal deformation also affects planetary orbits and axial tilts over time. As bodies exchange energy through tidal interactions, their rotations can slow down or speed up, and their orbital distances can shift. For example, Earth's rotation is gradually slowing down because of the tidal friction caused by the moon. As a result, our days are getting longer by about 1.7 milliseconds per century, and the moon is slowly drifting away at roughly 3.8 centimeters per year. Eventually, billions of years from now, Earth could become tidally locked to the moon, just as the moon is locked to us, meaning both would permanently show the same faces to each other. These tidal effects, while gentle on human timescales, are cosmic sculptors operating over eons. They smooth, stretch, and reshape worlds, ensuring that even in the grand stillness of space, motion never ceases. The tug of gravity between celestial bodies constantly redistributes energy, warps orbits, and remolds geometry. Every bulge, every elongated shape, and every orbital shift tells the story of two or more bodies locked in gravitational embrace. But tides aren't the only external forces capable of warping roundness. Impacts and collisions can have even more violent effects, reshaping worlds in moments rather than millennia. Asteroid strikes, comet impacts, and near misses can shatter symmetry and create scars that never fully heal. The moon's surface, for instance, bears countless craters, each one a frozen memory of a violent encounter that disturbed its perfect roundness. Even Earth, despite its active geology, still carries the remnants of massive impact basins like the one beneath Chicxulub in Mexico, which marked the extinction of the dinosaurs. Then there are magnetic and thermal forces. Strong magnetic fields can create surface irregularities or even influence the movement of molten cores, subtly altering shape over time. Thermal stresses, the expansion and contraction of material due to heating and cooling, can warp crusts, especially on tidally active moons like Io or Europa. These deformations are small, but they add to the universe's rich tapestry of imperfection. Ultimately, these external forces remind us that no object exists in isolation. Every planet, moon, and star is part of a gravitational network, a cosmic dance where proximity means influence. Perfect roundness is a theoretical ideal, but in practice, the universe is alive with subtle distortions, signs of motion, energy, and connection. Tidal forces, collisions, and magnetic influences don't destroy symmetry. They animate it. They turn static perfection into dynamic realism, showing that beauty in the cosmos often lies not in flawless geometry, but in the balance between order and disruption. In the next segment, we'll explore how composition, the material makeup of a celestial body, plays a critical role in how easily it becomes round or resists deformation. From solid rock to fluid gas and soft ice, the nature of a body's substance determines how easily it can become round. Composition, what a celestial body is made of, plays a profound role in determining how it takes shape. While gravity is the universal sculptor of roundness, the medium it works with, rock, metal, gas, or ice, determines how easily that shape can form. Two objects of similar size may end up looking very different simply because one is made of solid stone and the other of soft ice or flowing gas. The material composition of a planet, moon, or star essentially defines how willingly it yields to gravity's demand for symmetry.
At the heart of this lies a simple principle. Gravity pulls inward, but rigidity resists. When gravity acts on an object, it tries to draw every bit of matter toward the center of mass, aiming for a perfect sphere, the shape where all surface points are at equal potential energy. But not all substances respond equally to that pull. The degree to which a body can deform under stress depends on its material strength, its ability to resist compression, bending, or breaking. Let's start with rocky bodies, such as asteroids, small moons, and terrestrial planets like Earth and Mars. Rock is strong and brittle. It can withstand enormous stresses before deforming. In small celestial bodies, say asteroids only a few kilometers across, gravity simply isn't powerful enough to overcome that rigidity. As a result, these objects can maintain irregular, jagged shapes, like the asteroid Eros, which looks more like a peanut than a sphere. However, as the size of a rocky body increases, gravity's influence grows exponentially. Beyond a certain threshold, known as the potato radius, even rock begins to yield. This is the size at which a body's self-gravity becomes stronger than the structural strength of its material. For rocky objects, this critical radius is roughly 300 to 400 kilometers. Once a rocky body exceeds that size, it starts to pull itself into hydrostatic equilibrium, a nearly spherical shape. This is why Ceres, the largest object in the asteroid belt, with a diameter of about 940 kilometers, is round, while smaller asteroids like Vesta, 525 kilometers across, and Ida, about 30 kilometers across, are irregular. Now compare this with icy bodies, like many of the moons in the outer solar system. Ice is far less rigid than rock. It deforms and flows much easier under pressure. Consequently, icy objects can achieve roundness at much smaller sizes. The threshold for ice to become spherical is only about 200 kilometers in radius. For instance, Enceladus, one of Saturn's moons, is roughly 500 kilometers in diameter and beautifully spherical. Despite being relatively small, its icy composition allows gravity to smooth out its surface with far less effort than would be required for a rocky body of the same size. This contrast between rock and ice explains why so many small moons of the outer planets
appear rounded, while their rocky counterparts in the inner solar system do not. In the cold outer reaches of the solar system, ice behaves almost like soft clay in the hands of gravity. Over geological timescales, it flows and settles into equilibrium shapes, whereas in the warmer, rockier inner system, only much larger bodies like planets can achieve similar roundness. The gas giants, Jupiter, Saturn, Uranus, and Neptune, take this to an even more extreme level. Composed mainly of hydrogen, helium, and other gases, these planets are vast spheres of fluid under crushing pressure. They have no solid surface to resist deformation, which allows them to approach near-perfect roundness. In these giants, gravity and internal pressure act in a delicate balance, creating shapes that are almost perfectly symmetrical, except for the slight flattening at the poles caused by their rapid rotation. Their gaseous composition makes them ideal examples of how easily gravity can mold matter when rigidity is absent. However, the uniform roundness of gas giants masks complex internal structures. Deep within these planets, gases compress into liquid and metallic states under immense pressure. The outer layers remain fluid, but the core regions can behave more like dense rock or metal, introducing subtle variations in how the planet's mass is distributed. These differences affect the degree of flattening, the magnetic field, and even the way the planet rotates. For example, Jupiter's fast rotation causes it to bulge at the equator, while Saturn's lower density and even more rapid spin make it one of the flattest planets in the solar system. The same logic applies on an even larger scale with stars. Stars are made almost entirely of plasma, hot, ionized gas, which means they too can easily deform under gravity's influence. Because stars are in a constant state of hydrostatic equilibrium, with inward gravitational pressure balanced by the outward push of fusion-generated energy, they naturally assume a spherical shape. Their gaseous composition allows them to maintain this symmetry effortlessly, though rotation can again introduce some flattening. Even metallic composition, the presence of heavier elements like iron and nickel, influences how round a celestial body can become. In the early stages of planetary formation, heavier materials tend to sink toward the center, while lighter materials rise to the surface, a process known as differentiation. This layering enhances a body's ability to become spherical because the denser core strengthens the gravitational pull toward the center. The process of differentiation itself depends on the body's composition and temperature. Rocky planets, with molten interiors like early Earth, round themselves faster than cold, solid asteroids that never melted internally. In this way, composition doesn't just determine if a body becomes round, but also how fast it does, and how stable that roundness remains over time. A molten or semi-fluid object can quickly relax into a sphere, while a solid, rigid one resists reshaping, even under strong gravitational influence. This is why newly formed planets or moons, still warm from their creation, become round relatively quickly, while older, colder bodies can remain irregular indefinitely. Composition also dictates how external forces affect a body's roundness. For instance, tidal forces have a far greater effect on icy or gaseous worlds than on rocky ones. When Jupiter's immense gravity pulls on its moons, those made of ice or a mixture of ice and rock, like Europa and Ganymede, respond with visible deformation. Their surfaces crack and shift under the strain. But the rocky moon orbiting Earth, though also tidally locked, remains largely rigid with only slight tidal bulging.
Likewise, a planet's atmosphere, another aspect of its composition, can alter its apparent shape. Thick gaseous envelopes, like those of Venus or Titan, create smooth, rounded silhouettes, even if the solid body beneath them is less perfect. Gas and fluid layers blur imperfections, allowing gravity to assert a more uniform influence across a surface. Taken together, all of this shows that composition is the language through which gravity speaks. The same universal force acts everywhere, but the material it encounters changes the story. On hard, rocky worlds, gravity sculpts slowly, etching roundness only in the largest examples. On icy moons, it molds effortlessly, creating smooth, pearl-like spheres in the distant cold. And on gaseous giants and stars, gravity reigns supreme, forming near-perfect spheres that shimmer and spin in delicate equilibrium. Composition, then, is not merely a detail. It's the determining factor in how the universe's most fundamental shape comes to be. It explains why not all round bodies are equal, why some worlds bear the scars of resistance while others surrender gracefully to gravity's embrace. It's what gives the cosmos its incredible variety of forms, from jagged asteroids to perfect planets, from lumpy moons to luminous stars. In the next segment, we'll zoom out from individual worlds to a grander view, exploring how roundness itself is a universal pattern that repeats across scales, from the tiniest atoms and cells to the largest galaxies and cosmic structures. We'll see how this simple shape, born from balance and efficiency, is woven into the very fabric of existence. Roundness is not confined to planets or stars. It is a recurring theme that echoes throughout the universe, from the smallest subatomic particles to the grandest galaxies. When we look at the cosmos across scales, from the unimaginably tiny to the incomprehensibly vast, we find a striking pattern. Nature loves curves, not corners. Roundness, it seems, is the universe's signature of harmony, the most natural and efficient form that matter takes when left to its own devices. It's a shape that represents equilibrium, energy minimization, and the triumph of balance over chaos. To truly appreciate this universal pattern, let's start at the smallest scale, in the invisible realm of the atomic and subatomic. Atoms themselves, the fundamental building blocks of matter, are often depicted as tiny spheres. And while this visualization simplifies a more complex quantum reality, it captures an essential truth. In quantum mechanics, electrons exist not as neat orbits, but as probability clouds surrounding the nucleus. These electron clouds are most stable when they are spherically symmetrical, a result of the uniform distribution of forces acting on them. In other words, the energy configuration of an atom naturally favors roundness because it's the shape of lowest potential energy and highest symmetry. Even at the subatomic level, elementary particles like protons and neutrons are effectively spherical in nature. They are bound states of quarks and gluons, and while their internal structures fluctuate dynamically, their overall probability distributions remain roughly spherical. The same applies to electrons, which, as far as experimental evidence shows, have no measurable deviation from perfect roundness. The universe at its most fundamental level thus begins with symmetry, the spherical distribution of charge, mass, and probability. It's as if the idea of round is written into the quantum blueprint of existence itself. Zooming out to the microscopic biological world, roundness continues to dominate. Cells, for instance, are often spherical or roughly rounded in shape. This isn't coincidence or aesthetics, it's physics. The cell membrane, a flexible, semi-permeable layer, minimizes surface area for a given volume when it forms a sphere. This minimizes the energy required to maintain structural integrity while maximizing efficiency for nutrient exchange. When a drop of water forms inside another medium, it becomes spherical for the same reason. Surface tension pulls it inward, reducing the energy associated with its surface. In the same way, biological systems evolve toward efficient energy-saving configurations, and roundness, again, wins. Even at the molecular level, we see this pattern. Many molecules, particularly those involved in biological or chemical stability, adopt spherical or near-spherical geometries. Fullerenes, for example, carbon molecules composed of 60 carbon atoms, form perfect hollow spheres, earning the nickname buckyballs.
Soap bubbles, another everyday miracle, take on perfect spherical shapes because surface tension evenly distributes the forces across the thin film of liquid. These examples remind us that the sphere is not merely a cosmic shape, it's a universal principle of efficiency that governs matter at every conceivable scale. Now, if we move up to the planetary and stellar scale, we find the same logic playing out under different forces. Here, it's not surface tension but gravity that acts as the shaping agent. Gravity pulls matter toward the center of mass, erasing irregularities and enforcing symmetry as the object grows more massive. A small asteroid can remain jagged because its gravity is weak. A planet, far heavier, becomes round as gravity overwhelms its material strength. The result? Spheres once again. Planets, moons, and stars, all molded by gravity's unyielding preference for balance. But the story doesn't stop there. Beyond stars and planets, even entire galaxies display circular and spherical symmetries. Spiral galaxies, such as our Milky Way, are vast rotating disks of billions of stars, flattened by angular momentum, but still governed by gravitational equilibrium around a central bulge, itself roughly spherical. Elliptical galaxies, on the other hand, take on rounded, egg-like or football-like forms, reflecting the averaged-out motion of countless stars moving under mutual gravitational influence. On an even larger scale, galaxy clusters, immense groupings of hundreds or thousands of galaxies, also tend towards spherical distributions of mass and energy. Once again, roundness emerges as the equilibrium form of gravity on cosmic scales. And if we step back to consider the entire universe, cosmologists have discovered that even on this ultimate scale, the cosmos exhibits remarkable isotropy, uniformity in all directions. The cosmic microwave background radiation, or CMB, a faint afterglow of the Big Bang, shows that the early universe was almost perfectly uniform, with tiny fluctuations spread evenly in every direction. This isotropy implies a kind of large-scale roundness, not in a geometric surface sense, but as a distribution of matter and energy that is statistically the same no matter where you look. The universe in its infancy expanded outward uniformly in all directions, forming a spherical wave of creation, a symmetry that still echoes through space-time today. It's astonishing to think that this same pattern, roundness as the natural result of balance, manifests across a span of over 60 orders of magnitude, from subatomic particles smaller than a trillionth of a meter to galaxies spanning hundreds of thousands of light years. The underlying physics may differ, quantum forces, molecular interactions, gravity, but the outcome is the same. When forces act freely and symmetrically, the result is something round. Why? Because the sphere is the most efficient possible shape in three-dimensional space. It encloses the maximum volume for the minimum surface area, distributes pressure evenly across its form, and maintains stability under uniform forces. Whether it's surface tension at the microscopic level or gravitational compression on a cosmic scale, the sphere is the equilibrium state where energy is minimized and symmetry is maximized. It's as if every natural system, from atoms to galaxies, strives toward the same geometric truth. We can even find this pattern reflected in human perception and design. When engineers build pressure vessels, fuel tanks, or submarines, they favor spherical or rounded shapes because those forms distribute stress most evenly. Architects design domes and arches based on similar principles of stability and balance. Nature and human ingenuity converge on the same conclusion. Roundness isn't arbitrary. It's efficient, resilient, and universal.
In the end, this repetition of roundness across scales reveals something profound about the nature of reality. It tells us that symmetry, balance, and energy minimization are not just abstract concepts, they are the laws of being. The same physics that shapes an atom's electron cloud also governs the curvature of galaxies. From the tiniest droplet to the largest cluster of stars, roundness is the fingerprint of the cosmos, a recurring pattern etched into the framework of existence. Yet, despite this universality, the details of how roundness emerges vary with scale and force.
The next step, then, is to tie all of these scales together to summarize the physical principles that make this shape inevitable. We will explore how gravity, pressure, surface tension, and energy minimization all act as different expressions of the same underlying rule, the universe's perpetual drive toward balance and harmony. Throughout our exploration of the universe's roundness, from the tiniest droplets to the largest galaxies, one profound truth has emerged. Roundness isn't an accident. It's the inevitable result of fundamental physical principles working together in harmony. At every scale, nature follows a consistent logic, seeking stability, balance, and efficiency. The same few forces, gravity, pressure, surface tension, and energy minimization, orchestrate this grand symphony of shape, guiding matter toward equilibrium. Roundness is simply the most elegant expression of that equilibrium. Let's start with gravity, the most universal of all these forces. Gravity acts on every bit of matter, pulling it inward toward the center of mass. When an object is large enough for its self-gravity to dominate over the material's rigidity, gravity smooths out irregularities, drawing everything into a spherical form. This is because a sphere is the only shape where every point on the surface is at an equal distance from the center, meaning gravity pulls equally in all directions. It's the form of perfect inward balance. No side experiences a stronger pull than another. Planets, moons, and stars owe their rounded forms to this simple truth. Gravity, blind and impartial, erases jagged edges and uneven contours, sculpting worlds into symmetry. But gravity doesn't act alone. Within those massive spheres, another force comes into play: pressure. In stars and planets, pressure arises from the weight of overlying layers compressing the material beneath. In stars, for example, gravity's inward pull is counterbalanced by the outward pressure generated by nuclear fusion at the core. This delicate balance between gravity and pressure is known as hydrostatic equilibrium, a cosmic stalemate where collapse and explosion cancel each other out. The result? A near-perfect sphere. Without this balance, a star would either implode under its own weight or explode outward, losing its symmetry. The sun's roundness, then, is a visible testament to this internal balance, a perfect harmony between compression and expansion, gravity and energy. Pressure also plays a role in shaping planets and gas giants. Deep inside Jupiter or Saturn, gravity compresses layers of hydrogen and helium until they behave more like dense fluids than gases. The internal pressure from these fluids pushes outward, balancing gravity's inward pull, maintaining the spherical shape. Even Earth's solid layers experience this interplay. The pressure at the planet's core helps it stay stable and cohesive, maintaining its nearly spherical form despite tectonic activity or surface irregularities. Wherever matter can flow or compress under its own weight, gravity and pressure together will carve out roundness. Moving to smaller scales, where gravity's influence weakens, surface tension takes over as the dominant shaping force. In liquids, surface tension acts like an invisible skin, a cohesive force pulling molecules together at the surface. This happens because molecules at the surface have fewer neighbors to bond with than those inside the liquid, creating an imbalance. To minimize this imbalance, the liquid naturally contracts, pulling inward to reduce surface area. The smallest possible surface area for a given volume is that of a sphere. That's why water droplets, oil beads, and soap bubbles all take on perfectly rounded forms when free from external interference. The principle is identical to gravity's effect on large scales. It's all about minimizing differences, balancing forces, and reaching a state of least energy. Interestingly, surface tension and gravity share a philosophical kinship. They both act to minimize potential energy. In the case of surface tension, it's the energy associated with molecular bonds at the surface. In the case of gravity, it's the potential energy of mass distributed in a field. In both cases, the system evolves toward the same outcome, a configuration where forces are evenly distributed and energy is minimized. That's why a droplet of water floating in zero gravity, a planet orbiting a star, and even a star itself all tend toward the same shape. Whether the dominant force is molecular cohesion or gravitational attraction, the sphere is the endpoint of energy optimization.
This brings us to the overarching principle connecting them all: Energy minimization. In physics, every system naturally seeks the lowest possible energy state, the configuration that requires the least effort to maintain. The sphere, mathematically and physically, represents this ideal. It encloses the greatest volume with the smallest surface area, spreads forces evenly in all directions, and requires no preferential axis or orientation. That's why, whether it's a soap bubble, a molten droplet, or a massive star, roundness always emerges when nothing is forcing the system to favor one direction over another. Energy minimization doesn't just explain why things become round, it also explains why they stay round. Any deviation from a spherical shape introduces additional stress, uneven forces, or excess energy into the system. A bump or bulge on a planet increases gravitational potential energy because more mass is farther from the center. A dent on a droplet increases surface area, raising surface energy. In both cases, nature corrects these deviations, smoothing them out over time as the system returns to its lowest energy configuration. That's why planets can retain their roundness for billions of years, and why even tiny droplets will quickly reform into spheres when disturbed. When we consider these forces together, gravity, pressure, surface tension, and the universal drive for energy minimization, a profound unity emerges. They are all, at their core, expressions of the same fundamental tendency, the universe's desire for balance and symmetry. Each operates at a different scale and through different mechanisms, but their goals align perfectly. Gravity acts over vast distances, pulling celestial bodies into shape. Pressure works internally, ensuring those shapes remain stable. Surface tension sculpts the small-scale world of fluids and bubbles. And energy minimization serves as the grand rule that ties everything together, the cosmic imperative toward equilibrium. This harmony of forces explains why roundness recurs across every level of reality, from the atomic to the astronomical, from quantum probabilities to planetary forms. Roundness is not just a coincidence, it's the inevitable outcome of the universe's laws. The same mathematical elegance governs the droplet on a leaf and the blazing sphere of the sun. It's as though nature has only one answer to the question of stability, repeated endlessly in different languages of physics. Yet, while these forces strive for perfect symmetry, the universe also allows for imperfection. Rotation, collisions, magnetic fields, and other influences suddenly distort roundness, giving each world its individuality. And that's what makes the cosmos so rich. Beneath the diversity of forms lies a unifying simplicity, a shared geometry written into the laws of nature. In the next and final segment, we'll reflect on this deeper meaning, exploring how roundness is more than just a physical consequence. It's a symbol of balance, order, and beauty. We'll conclude by looking at the philosophical side of the story, why the sphere, more than any other shape, captures the essence of the universe itself, a timeless expression of unity within diversity. As we reach the end of this journey through cosmic geometry, one truth shines brighter than all others. Roundness is not merely a coincidence, nor is it an aesthetic preference of nature. It is the physical embodiment of balance, symmetry, and harmony, principles that underpin everything from the smallest atom to the largest galaxy cluster. When we look at a round planet suspended in the dark expanse of space, what we are really seeing is the visible manifestation of the universe's eternal drive toward equilibrium. The sphere is not just a shape, it is the universe in its most peaceful state. There's a quiet poetry in this realization. Think about it. Every round object in the cosmos, whether a droplet of rain, a glowing star, or a distant exoplanet, has arrived at its form through struggle and resolution. Gravity pulled it inward, pressure pushed it outward, energy found its minimum, and the result was harmony. Roundness is the resolution of conflict. It's the shape the universe takes when all opposing forces reach agreement. That is why roundness recurs across scales, time, and matter, because it represents the final, most stable answer to nature's question: how can energy, mass, and space exist in balance? This insight reveals something profound about the nature of existence itself. The laws of physics, those invisible rules that govern motion, force, and energy, seem to have a deep appreciation for symmetry. From the structure of fundamental particles to the grand architecture of galaxies, symmetry is everywhere. And symmetry, in its purest three-dimensional form, gives us the sphere. It is no exaggeration to say that roundness is written into the code of reality. It's the universe's favorite solution, elegant, efficient, and enduring. But beyond the scientific explanation lies something deeply philosophical. The sphere isn't just a stable shape, it's a symbol, a metaphor for completeness. Every point on a sphere's surface is equal. No part is privileged or neglected. There are no edges, no beginnings, no ends. It represents total inclusion, total unity. That's why ancient civilizations and philosophers, long before they understood gravity or pressure, revered the sphere. To them, the heavens were round because roundness symbolized perfection. Aristotle called the sphere the most divine of shapes, believing celestial bodies must be spherical because perfection belonged to the heavens. The ancient Greeks carved their cosmology around it, and in a way they were right. Not for mystical reasons, but because the laws of physics themselves are built upon the same ideals that ancient thinkers associated with divinity: order, balance, and symmetry. Consider how deeply this pattern of roundness is ingrained in our perception of beauty and harmony. From the human eye and Earth's moon to pearls, bubbles, and even seeds, we find comfort and fascination in curves. A circle feels complete, satisfying, and eternal. Artists, architects, and scientists alike have all drawn inspiration from it. The Renaissance thinkers saw in the circle and sphere the reflection of cosmic order. Engineers still use those forms to achieve balance and strength. Even in our language, we equate roundness with wholeness. Well-rounded, full circle, coming around. The shape's universality has permeated not only physics, but also consciousness itself.
There's also a humbling aspect to this universal pattern. Roundness reminds us that, in the grand scheme, we are part of something profoundly consistent. The same forces that molded the stars molded the atoms in our bodies. The same drive towards balance that shapes galaxies also shapes a single raindrop. We are built from the same laws that shape worlds, each of us, in a literal and poetic sense, made of stardust, obeying the same physics. When you hold a marble in your hand or watch a soap bubble drift in sunlight, you're witnessing the same principle that governs entire solar systems. The microcosm mirrors the macrocosm, different in scale, identical in law. And perhaps that's the most awe-inspiring realization, that the universe, vast and chaotic as it may seem, is fundamentally ordered. Roundness reveals that order. It's nature's signature of peace, a quiet statement that, even amid all the forces and turmoil, balance is possible. Whenever energy finds harmony, whenever chaos yields to symmetry, the result is something round. This brings us to a deeper reflection. Roundness is not only a scientific inevitability, but also a philosophical truth. It tells us something about the way the universe prefers to exist, not in jagged extremes or sharp divisions, but in continuous, inclusive harmony. This sphere, by being the most stable and uniform shape, becomes a symbol of unity itself. It has no corners to break, no edges to fray. It endures because it embraces all directions equally. In a sense, the roundness of the universe reflects the roundness of time and life. The stars are born, live, and die in cycles. Planets form, erode, and reform. Galaxies merge, evolve, and expand. Even our understanding of existence tends to return to its origins, learning, questioning, rediscovering. Just as the sphere has no beginning or end, the story of the universe is one of endless renewal. So when we gaze upon a planet's curved horizon or marvel at the perfect symmetry of a bubble, we're not merely observing physics in action. We are glimpsing the very nature of creation. Roundness is the universe's way of whispering that balance is beauty, that simplicity is power, and that all things, in their purest state, tend towards harmony. In the end, the roundness of the cosmos is more than a shape. It's a philosophy encoded in matter itself. It reminds us that nature does not chase perfection for appearance's sake, but because equilibrium is the foundation of existence. Every atom, every droplet, every world carries that truth within it. The universe is round because roundness is what happens when everything, force, energy, and matter, finally agrees. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.